Hello everyone and welcome to the 2021 Algebra 1 Regents Review by eMath Instruction. I'm Kirk Weiler, and for the next couple hours, maybe up to 3 hours, just depends on how long it takes me to do the exam, I'm going to be walking through the June 19th, 2019 Algebra 1 exam. This was the last summer exam given before the pandemic. There were a couple more exams given, but then the ones last year were canceled. Now, we mentioned this in a previous live announcement, but if you'd like to get a copy of the exam, you can go over to our site, that's emathinstruction.com. You can click on our blog. The first article in the blog, Algebra 1 Live Regents Review, click on that. And then you can scroll down where you can both find a link to our YouTube channel, which you probably don't need if you're watching us, and you can find a link to the exam itself. If you click on that link, it'll open up the exam that I'm going to be working on tonight. You can print it out, or you could just be looking at the problems as I go through them. But it's always helpful to have your own copy in front of you because you can just work with it and you can see it a lot better than mine. Anyhow, let me close that out. Additionally, of course, some of the problems tonight are going to require the use of a graphing calculator. We're going to use the TI Inspire calculator tonight. Now, there's lots of different calculators that are out there. You could easily, hopefully my TI Inspire is going to open up. You could easily be using the TI-83, the TI-84, and I apologize because this is a very different operating system than either of those two. But from what we understand, the most used calculator right now in Algebra 1 classes is the TI Inspire, so we're going to be using this calculator a bit to do some of the work that we have on this test tonight. All right, well, without further ado, let me minimize this screen. Let's get to it. The Algebra 1 Regents exam. It's been a little while since I've done an algebra exam, so let's see how this one goes. All right, we're going to start off with the multiple choice questions, right? Each multiple choice question on the Regents exam is worth 2 points, that is unscaled. And our first question tonight, the expression w to the fourth minus 36, let me make my pen width a little bit bigger, is equivalent to which of the following? All right, now the first thing that we should do is we shouldn't get scared by that w to the fourth, all right? In fact, looking at all of the choices, right, it's very clear that what they're asking us to do in this situation is to factor, right? What we want to do is factor this expression. Now, again, the w to the fourth could scare you a little bit, except that this really has exactly the same structure as x squared minus 36. Now, if you've done some factoring in Algebra 1, this is what's known as the difference of two perfect squares, right? X squared is a perfect square and 36 is a perfect square. And if you've done one of these, you've kind of done them all, right? This thing factors into x plus 6 times x minus 6. Now, likewise, our expression, w to the fourth minus 36, we can use that exact same structure, and we can say that that's going to be w squared plus 6 times w squared minus 6, right? We should know from exponent properties that w squared times w squared, right? Add the two exponents, and you get w to the fourth. And there it is. This expression is equivalent to this one, and that would be choice 4. All right, let's keep going. I feel like I want a width that's somewhere between the biggest one and the smallest one I have here, but that's okay. Here we go, number 2. If f of x equals 4x plus 5, what is the value of f of negative 3? All right, this is what's known as function notation. We're going to talk about functions a lot more in number 3, way more than you ever wanted to. But basically, these are the kind of problems that we'd want 30 of them on the test, right? All we need to do is take the input, which they show in parentheses here is negative 3, and we need to substitute it in for x and do whatever that function rule tells us to do. And specifically, this function rule tells us to take the input, multiply it by 4, and then add 5. So literally, f of negative 3 is going to be 4 times negative 3 plus 5. Remember your order of operations, that multiplication comes first. 4 times negative 3 is negative 12 plus 5. You know, I thought I'd just do the 5 in red for the fun of it. And that gives us negative 7. If you've never watched an eMath video before on my smart board up here, you're going to notice every once in a while the pen's just going to change from whatever color it's in to red. In this case, red on the 5. All right, let's take a look at number 3 where we really dig into the concept of what a function is. Right? Number 3 says, which relation is not a function? Now, relations in math basically just relate, literally, two variables. You can think of them conveniently as x and y, whatnot. A function, though, is a very special type of relationship because basically what a function is when a value of x goes in, a single value of y comes out. Or, more generally, when the input goes in, a single output comes back out. One of these 4 relationships, therefore, violates that idea. Okay? Let's take a look at choice 1. In choice 1, we've got a relationship given in a table. I shouldn't say a function yet because I'm trying to figure out whether it is one or not. Now notice in here, none of the x values, -10, -6, -2, 1, and 5, none of those x values repeat. All right? And that means it's a function. This is a function. Why does that mean it's a function? Well, just think about this. Let's say they threw in an extra little thing in here, right, where maybe they had x = 1 show up again. And let me put as an output 5. Right, this would no longer be a function because an input of 1 would have both an output of 9 and an output of 5. But in this case, because none of the inputs got repeated, every single one of them only has one output. So that is a function. Now let's just stick up here and take a look at choice 3 instead of going down to choice 2. Choice 3 is a relationship given in a graph. Now again, it's all about whether every value of x gets only one value of y. Well, let's pick a value of x. Let's go out to x = 3 here. Well, on this graph, right, when x is 3, y is equal to 2. There is only one y value that goes with an x value of 3 or an x value of 2 or an x value of 1, whatever. Now, some of the y values repeat, but that's completely okay. In a function, every x gets only one y. So you might say, how could a graph of a relationship ever not be a function? Well, let's say you had something that looked like this. Let's take this exact graph, but kind of like flip it on its side, right? This would no longer be a function because, let's stick with our value of x = 3. If we went to x = 3, then what would happen is that there would be 2 y values, 2 outputs that go with this. This is what's called the vertical line test for the graph of a function. If any vertical line, only hits the graph once, it's a function. But if a vertical line hits the graph more than once, it's not a function. Now again, we're trying to find the one that's not a function. And I got to go through all of them because quite frankly, the answer is going to be number 4. But let's take a look at number 3 real quick and understand why that's a function. Right, this almost doesn't look like a function. It just looks like an equation with 2 variables in it. 3x + 2y = 4. But again, remember the idea is if I put in a value of x, some random value of x, will I get more than one value of y out? Well, let's pick something. Like let's say I put in like x = 1. If I put x = 1 into that equation, and I solved for the output, y is the output, right? Then I would have something like this. I'm doing a lot of this solution sort of in my head, but I'd get y = 1/2. In other words, a single value of x resulted in a single output, right? Y = 1/2. So that is definitely a function as well. So now let's understand why 4 is not a function. Now it's not a function because it's got letters involved. That was horrible, okay? But it's the only way I can put it. It's not a function because of the letters. No, it's not a function because this input of 2 went to an output of A and an output of B. A single input gave 2 different outputs, A and B. I kind of wish in this problem they had actually just had numbers over here as well. Why they had to suddenly throw letters into choice 4 is beyond me. But it is true, functions do not need to be numerical. They can have as an input something like, let's say, a person's name, like my name, Kirk, or just a person. And then maybe the output is their middle name, right? Everyone basically has one middle name. All right, so functions don't have to be numerical, and the idea here is this isn't a function because this input went to 2 outputs. So there's our winner. Choice 4. All right, so everybody got that from the first page of the exam, right? We've got, if you've done the exam already, number 1 was 4, number 2 was 2, and number 3 was 4 again. All right, let's take a look at number 4. Here we go. Given f of x equals x minus 2, the quantity squared, g of x equals x minus 5, the quantity squared, plus 4, plus 4 also in the first one. When compared to the graph of f of x, the graph of g of x is what? All right, so let's talk about this problem a little bit. Now, there's a lot of different ways to do this problem. Okay, lots of different ways, some of them quicker, some of them slower, all right? But one thing that we have to understand up front is the idea that we've got this function that has some graph, and we'll talk about that in a little bit. And then we want to know how the graph of the second function, how the graph of g of x compares to the graph of f of x. Now, one thing that you studied, and we're going to actually see it later on in the test, is something called the vertex form of a parabola. And if you already know everything about the vertex form of the parabola, this is a very easy problem, because you can look at this particular one and you can say, oh, it's got a vertex at 2, 4. And you can think about this one, oh, it's got a vertex at 5, 4. So what does that mean? Well, it means that this one must have gotten moved to the right 3 units in order to match up with this one. So that would be shifted 3 units to the right. So choice 2 is our correct answer. But that requires, of course, that you're very firm with the idea of what the vertex form of a parabola is. And as I said, it's going to come up again. Or you could also just understand generally how shifting works, right? This function is exactly the same one as the first one, but we've subtracted an additional 3 from the x, moving it 3 units to the right. But finally, and never forget this, you have 3 hours for this test. 3 hours. And you've got a calculator. So let's open up the TI Nspire real quick for the first time, and let's take a look at these 2 functions on the graphing calculator. All right, here we go. So I'm going to add a graph. I'm dying to do this. Here we go. F of x, let's put in that first function, x minus 2 squared plus 4. All right. And by the way, let's just take a look at this function real quickly before we put in the other one. As I noted before, this thing has a vertex at the coordinate point 2, 4, and you can kind of see that, right? If I go out to 2 and I go up to 4, there's my vertex, my turning point of the parabola. Now let's put in our secondary function, menu. Let's see, graph entry. I want a function, f of x2 is going to be, now I know that it says g, but I don't really have a lot of choice here. I got to put it in as f of x2. Don't forget that squared button. You'll get a line if you don't have the squared. And there's my second function. And again, we can see directly on this calculator screen that these 2 are exactly the same function, right, in terms of their shapes, right? They're the same shape. But the red one is the blue one after it's been shifted over by 1, 2, 3 units. Again, if you can't exactly tell that from the calculator screen, you could go through using the calculator's minimum command to find where that vertex is, and then you'd be right back to where we were at right here. But either way, g of x is f of x shifted 3 units to the right. Choice 2. I'm going to get a little drink of lemonade. I love my lemonade during my review sessions. It keeps me going. Actually, I just get paid by the National Lemonade Council of America to spout things about them. Pretty sure there isn't a National Lemonade Council of America, but you never know. There's probably some lemonade organization out there, something, you know. They probably have conferences. It's a good time. Anyway, let's take a look at number 5. Students were asked to write 6x to the 5th plus 8x minus 3x cubed plus 7x to the 7th in standard form. Shown below are 4 student responses, one from Anne, one from Bob, one from Carrie, and one from Dylan, because, you know, we're in the Midwest. Which student is correct? All right, so what this problem really is about is what does it mean to put a polynomial, which is what this thing is, it's a polynomial, in standard form. All right, so it's basically just purely, do you know what that means? Let's forget about Anne, Bob, Carrie, Dylan, and all the rest of the Beatles that are up here, and let's just talk about this particular polynomial and what standard form means. All right, so with standard form, right? We have 4 terms here, and we're going to take the one with the highest power, which is 7x to the 7th, and we're going to write it first. And that pretty much tells us what the right answer is, and yes, Anne, you're the winner. But we're going to take this thing, and we're going to include the sign with it. In other words, that's a positive positive 7x to the 7th. Then we're going to find the next power, and that's a positive 6x to the 5th. We're going to find the next one, which is a negative 3x cubed, and the final one, which is a positive 8x. You know, I was kind of hoping that at least Bob, Carrie, or Dylan would know that you had to put the highest power first, but none of them even knew that. So Anne got it like right away, right? Anne is right for choice 1. Okay, let's take a look at problem number 6. The function f is shown in the table below. X equals 0, 1, 2, 3, f of x equals 1, 3, 9, 27. Which type of function best models the given data? All right. Now, you've studied quite a few functions in this course. You have. But there were 3 major ones you should have looked at, right? And the 3 major ones were linear, those that have graphs that are lines, exponential, that's a long word, and those that kind of curve up like this or curve down like that, and quadratic. Those are the major kinds, and that just, anyway, that quadratic. And those are parabolas. We just saw a couple of those, and we'll see some more as we move on. Now, in this particular problem, it's just between linear and exponential, right? So choice 1, an exponential growth function. Choice 2, an exponential decay function. By the way, this is an exponential growth. This one's an exponential decay, right? Then a linear function with a positive rate of change. That would be one that has a positive slope. And then a linear function with a negative rate of change. That would be one that actually kind of looks like that. Now notice, right, as x gets larger in this table, so does f of x, so does the output, the y, right? This is just another name for y, all right? So it's definitely not an exponential decay function, and it's definitely not a linear function with a negative rate of change, right? Those two would both be functions that decrease, and this is an increasing function. So it's either an exponential growth function or it's a linear function with a positive rate of change. In other words, they could have just said a linear growth function, but for some reason they didn't. Anyway, so an exponential growth function is our winner, and let's take a look at y, right? You should notice that from one y value to the next, what's happening is that the output is getting multiplied by 3, and that is the hallmark of exponential growth, or exponential decay, right? In exponential growth, what happens is that we're multiplying by a number that's greater than 1 to get to the next output value. In an exponential decay function, something like this, we would be multiplying each output by a number between 0 and 1, like 1/2 or 1/3 or 0.75, something like that. Now, it's really also quite important to understand why it's not a linear function, right? Why it's not a linear function. So just for a moment, even though we know that the answer is 1, it's a little warm right now, even though we know that the answer is 1, let's talk about why we can tell right away it's not linear, all right? In a linear function, when you have x's that are equally spaced, right? These are equally spaced x's, they go up by 1 each time, then what happens is that your y's should also be equally spaced. They should go up by the same amount each time. And yet, to go from here to here, we would add 2. To go from here to here, we would add 6. To go from here to here, we would add 18, right? And that tells you right away it just can't be a linear function, right? The slopes would be different. The slope between these two would be 2 over 1, here it would be 6 over 1, here it would be 18 over 1. Not linear. Definitely exponential. All right, one of my least favorite questions on the test, number 7. Which expression results in a rational number? All right, let's talk about rational numbers. Okay, look, rational numbers are probably numbers that you would consider to be normal, I guess. I don't know. I don't know what you consider to be a normal number at this point, probably just 0, 1, 2, 3, 4, things like that. But rational numbers are numbers that can be written as fractions, right? They're also numbers that happen to have either terminating decimals or decimals that repeat, right, in some kind of predictable pattern, like 1/3, 0.33333333, etc., right? So those are rational numbers. Then you have irrational numbers. Those are numbers like pi, right, that have decimal expansions that go on forever to infinity and beyond, and they never have a repeating pattern in any way, all right? Now, one of the things that you should have learned in this course were that square roots, which is why they're showing up all over the place in this problem, square roots of non-perfect squares, non-perfect squares are basically numbers that have obnoxious square roots, but square roots of non-perfect squares are irrational numbers, every single one of them. So the square root of 10 is irrational because it's 3 point something, da 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 da. The square root of 50 is irrational, right? And no nice number times a nice number is equal to 50, all right? So every square root actually that shows up in these problems is an irrational number. So how do we get a rational number out of them? Well, you were supposed to learn all these different rules this year. For instance, like a rational number, 5's a rational number, times the square root of 5, that's an irrational number, is an irrational number. You were supposed to learn that a rational times an irrational is irrational, or it's supposed to be a non-zero rational times an irrational is irrational. So you're supposed to know right away that's irrational. Now here I have square root of 2, which is irrational, plus square root of 2, also irrational, and you were supposed to learn that when you add an irrational number to another irrational number, it is an irrational number, assuming that they don't add out to be 0. It's true. Anyway, actually there could be other cases, but let's not go there. And the same thing is going on here as well. Okay, now where a lot of people boil down to, and to doing this problem, is that they know that if you just type the thing into your calculator and you get some kind of nasty decimal that goes on forever and doesn't doesn't terminate or repeat, well then that's irrational. So you would just start by cranking through these. And in fact, let's take a look at the first one on the calculator, the square root of 2 times the square root of 18. Let me bring up the TI Nspire again, and let me bring in, okay, I gotta actually insert a little calculator window here. And what do we have? We had the square root of 2, oh, that's not what I wanted, times the square root of 18. Oh no. Oh, there we go. Thank goodness for touchscreens. And take a look at that. The square root of 2 times the square root of 18 is 6. That's a rational number, right? It's got a decimal that terminates. It's 6.0. Done, right? Or if you want, it's 6.0 repeated and done. Either way, right, 6 is a rational number. So it's that first expression, that first one right out of the gate, that's the correct answer. And the reason for that is that square roots love multiplication. What do I mean by that? The square root of 2 times the square root of 18, well, you can actually multiply the 2 and the 18 together and then take the square root. And 2 times 18 is 36, and the square root of 36 is 6. Now, of course, they didn't have to make it work out that way. They can do a lot of different tricky things to try to throw in the one rational number or the one irrational number, either way. So you could play around with a little bit of that, like put the thing in and see if the decimal repeats. So like for instance, let's take a look at like choice 2 and then we'll move on to number 8. Choice 2 is 5 times the square root of 5. So if I put that into the calculator, all right, and I hit enter, what I ended up seeing is I end up seeing a decimal that has no discernible repeating pattern, right? 11.18033988875. And a lot of teachers will say, that's the way to do it. You know, put the expressions in, see if the decimals repeat or terminate, and if they do, they're a rational number, and if they don't, they're an irrational number. And you know what? It's not a bad way to do it. Let's take a look at the next problem. Number 8. A polynomial function is graphed below. Which function could represent this graph? All right, so this brings us to the first time when we're going to see a very important concept of algebra, all right? And that's what's known as the zeros of a function, right? The zeros of a function are literally the x values where the function crosses the x-axis. That's at -2, 1, and 2, right? So the zeros are where a function intersects the x-axis. Another name for the zeros are the x-intercepts. And those occur on this function at x equals -2, x equals 1, and x equals 2. Now, think about all those quadratic equations you solved during the year, where you had to factor things and then take each factor and set them equal to 0. Well, we can kind of go in the opposite direction, meaning that for each one of these zeros, there is a binomial factor that goes with it that, if you will, kind of is like, it almost looks like it's the opposite of each zero. In other words, the factor that goes with x minus 2 is x plus 2. The factor that goes with x equals 1 is x minus 1, and the factor that goes with x equals 2 is x minus 2. So this is the factored form of the correct function. I'm just going to put a little y equals in front of it. Now, if you look, though, at the 4 choices, none of them apparently looks like this. And it's kind of like, wait, what? You know, he's got 3 factors up here, and there's only 2 here. But notice in each one of these cases, one of the 2 binomial factors has an x squared in it. Now remember way back to problem 1, right, where we had w to the 4th minus 36, and we factored it as w squared plus 6 and w squared minus 6? Well, we can kind of do the same thing here, except we can take these 2 binomials, we can multiply them together. I'm just going to write that x minus 1 first. We can multiply these 2 together to get x squared minus 4, right? So we now have y equals x minus 1 times x squared minus 4, and that's our winner right here. Now, that is a very, very important concept in Algebra 1, the connection between the zeros of a polynomial and its factors, okay? A critical idea. But I do want to, again, come back to the fact that when push comes to shove, if you were looking at this problem and you had just no idea how to get the correct answer, why not graph each of the 4 choices? Why not? In fact, let's just take a look at a graph of the graph of the correct choice on the TI Nspire and one of the ones that's incorrect, right? So let's go back to our TI Nspire. I'm going to close out this window. I don't think I want to save it. Let's go to a graphing window, and let's put in the correct one first. That was choice 3, x minus 1 times x squared minus 4. Correct? Yep. Enter. And look at that. Yep. Right? That's exactly the graph. Let me just switch back over to this really quick. There it is. Go back to our TI. There it is. Bingo. Right? And look at those zeros, right? X equals -2, x equals 1, and x equals +2. Now let me just throw in for a second an incorrect choice. I'm just going to go right back in here. And let's delete that out. I probably could have just cleared it. Let's do f of x equals, no, I don't want to, y equals, oh, come on. All right, no, start new there. Let's do choice 1, where we've got x plus 1 times x squared plus 2. Right? That's choice 1. It's pretty easy to put this in your calculator. It doesn't matter whether you have a TI Nspire, a TI-83, a TI-84. It really doesn't matter. You could have a Casio even. You know, the plain fact is, when you put this equation in its nicely factored form, and you graph it, it simply doesn't look like this one. End of story. So we should use technology where we can. Now again, I hope that you understand the idea. It's going to come up again in another problem, all right? The idea between the connection between the zeros and the factors. But it's good to be able to just know that you're right by graphing it on your calculator. All right, let's take a look at problem number 9. Oh, we had a little focus thing there. All right, number 9. When solving p squared plus 5 equals 8p minus 7, Kate wrote p squared plus 12 equals 8p. The property she used is, which of the following? All right, well, let's just think about what Kate did for a second, right? Kate starts with this equation. P squared plus 5 equals 8 4p minus 7, right? And then somehow she gets down to this. Well, the way Kate would have gotten from here to here is by adding 7 to both sides, which is a very understandable thing to do, right? You want to clear out that 7, and then you're just going to get 5 plus 7 is 12 equals 8p. So what did Kate do? Well, Kate added 7 to both sides of the equation. We can add or subtract the same number from both sides of the equation anytime we want in algebra due to what's known as the addition property of equality, right? Likewise, if we either multiplied or divided both sides of the equation by the same number, that would be the multiplicative or multiplication property of equality. Mouthful. All right, you could have 4 of them. You could have the addition property, the subtraction property, the multiplication property, and the division property. But typically the addition, subtraction are just addition, and then the multiplication, division are just multiplication. These other ones, the associative, commutative, and distributive properties, never go across the equal sign. They're just things that you do to one side or the other to simplify the algebraic expression that's either on the left or the right. But in this case, we definitely used the addition property of equality. All right, I think it's time for another drink of lemonade. Ah, so good. All right, let's take a look at number 10. David wanted to go on an amusement park ride. Don't we all? Especially after the last year we've been in. A sign posted on the entrance read, "You must be greater than 42 inches tall and no more than 57 inches tall for this ride." Which inequality would model the height, x, required for this amusement park ride? All right, let's take a look. Well, this is what's called a compound inequality. There's 2 conditions that must be met simultaneously. One, got to be greater than 42 inches. All right, that's pretty straightforward. No more than 57 inches. That's a little trickier. No more than 57 inches. So you couldn't be 58, you couldn't be 59, you couldn't be 72, 74 like I am, right? No more than 57 inches. This must be a very small ride. No more than 57 inches tall, now that I think about it. All right, could you be 57? Yes, right? You just can't be more than 57. So, besides that, right, we also have the condition that x is less than or equal to 57. All right. Now, notice right away the word "and" there. X has got to be greater than 42, right? You've got to be more than 42 inches tall, and you must be less than or equal to 57. So immediately these 2 with the ors are gone. They're gone. Or means, look, you got to either be greater than 42 inches tall or less than or equal to 57 inches tall. By the way, that would be everything, right? If this was an or instead of an and, that would be everything, because I'd be like, well, I'm taller than 42 inches. And somebody else that was like 3 inches tall, very short, right? They'd be like, well, I'm less than or equal to 57 inches. So these ors are out. Ors mean that one of the conditions has to hold or the other one, but they don't both have to hold. We got an and situation here, right? So these 2 are out. Now, that means it's one of these 2, okay? And I actually kind of object to this answer even whatsoever being on this test. This is mathematical gibberish. This says 42 is greater than x and x is greater than or equal to 57. You give me the number that fits that description. You give me a number where x is both less than 42 and greater than or equal to 57. That number doesn't exist, right? It's this one, right? X is greater than 42 and at the same time less than or equal to 57. Anytime you've got an and inequality, you join them into a single statement. An or has to be written separately like that. All right, let's take a look at number 11. Hey, we're back to linear functions, number 11. Which situation can be modeled by a linear function? Okay, now remember, we talked about this a little bit before when we saw that one table problem. The key for a linear function is that equal changes in x, equal changes in the input, must result in equal changes in the output. So if I add 3 to x each time, then maybe I have to add 5 to y each time. But it's these constant additions or constant subtractions. So choice 1 says the population of bacteria triples every day. Well, that's not a constant adding, right? That's an exponential function, right? If I'm going to multiply or divide by the same amount each time, that is exponential. Let's take a look at 2. The value of a cell phone depreciates at a rate of 3.5% each year. Well, quite frankly, as soon as you see percent, that's again exponential, right? Depreciating at a rate of 3.5% each year, you got like one of these kind of curves, right? One of these decreasing exponential curves. Take a look at number 3. An amusement park allows 50 people to enter every 30 minutes. Well, there's our winner, right? Every 30 minutes that goes by, that's our input, let's say, our output, which is the number of people in the park, goes up by 50. That's literally the slope, right? It's the rate. 50 people per 30 minutes. Or, 100 people an hour. Whatever, it's all the same thing. But yeah, right? That's our linear, right? For this constant change in the input, we get this constant change in the output, and that's why linear functions have slopes. All right. Oh. Just for the record, number 4, a baseball tournament eliminates half of all the teams each round. That's again an exponential, right? Think about it. You've got like the NCAA tournament starts with 64 teams, then 32, then 16, then 8, then 4, then 2, then 1, right? And that's not a constant change. I mean, yes, we're halving each time, but each time the change is, well, changing. All right. Let's take a look at number 7. Jenna took a survey of her senior class to see whether they preferred pizza or burgers. The results are summarized in the table below, right? Which are broken down by cisgenders. Anyway, one of these days. So we got, all this survey, right? We got male, broken into male and female, broken into whether they like pizza or burgers. And the question is, of the people who preferred burgers, approximately what percent were female? Now, as soon as they say something like, of the people who prefer burgers, you know what I'm going to do? I'm going to just I don't care, right? And we're not even thinking about the pizza people. They're not even in our consideration. Of the people who preferred the burgers, approximately what percent were female? Well, how many people preferred burgers? Well, there were 42 men, 26 women, or females, 42 male, 26 female. So we have 68. That almost looks like an 8. We have 68, right, people that preferred burgers. What percentage of them were female? Well, we should know how to do a percentage problem with just a fraction. We can do the number that were female divided by the total number that we're considering, and those are only the people that like the burgers. Right? We can now crank this into our calculator. I'm going to save a little time and not go over to the TI Nspire on here. Although, maybe I will. Let me go real quick. Insert calculator. What do I got? I've got a different sheet. 26 divided by 68. Enter, which is 13/34. The Nspire is kind of funny. It forces you to say what the decimal is. So the decimal becomes 0.382359, and hopefully you all know that if you've got a decimal of 0.382, that you could multiply this by 100 to get 38.2%. Right? But the real key in this problem, right? The real key in this problem is first saying, well, look, of the people who preferred the burgers, right? We don't care about the pizza here. This is what's called a conditional relative frequency. The condition is that we're only thinking about people who were eating or preferred the burgers. And then we're asking, well, what proportion or percentage of those people fell into the female category? All right, let's take a look at number 13. When 3a plus 7b is greater than 2a minus 8b is solved for a, the result is which of the following? All right, so to begin with, this can look awfully confusing because of all the a's and b's and things like that. At the end of the day, though, keep in mind we're still going to be just doing all the steps we always do to solve an inequality, which are all the steps we do to solve an equality. There's just one little tricky scenario, which actually doesn't even come up here. It comes up in a later problem, but not in this one. Anyway, so let's take a look at this. I'm going to write down the problem again. 3a plus 7b is greater than 2a minus 8b. All right, now I want to solve for a, which generally means I want to get everything with an a on one side and everything without an a on another side. All right, my board just blipped, I don't know why. Anyway, I got 3a minus 2a, which is a, plus 7b, whoops, I don't know why that greater than became an equal, is greater than negative 8b. Now to isolate that, I'm going to subtract a 7b from both sides. And that's going to be a is greater than, let me just scroll this up, negative 8b minus 7b. Look, if negative 8 minus 7 is negative 15, then negative 8b minus negative 7b, if I can write a 15, is negative 15b. And that's it. A is greater than negative 15b. Now, one of the things that's a little bit unfortunate, because I would have liked to have talked about it in this problem, is that the only real difference when solving a linear inequality compared to a linear equation, linear meaning it's just x to the first, there's no x squared, x to the third, square root of x, none of that, right? Is that if you divide or multiply both sides of the inequality by a negative, and by the way, 99% of the time it's dividing both sides by a negative, not multiplying. But if you divide both sides by a negative, the inequality sign switches. The inequality symbol switches from a greater than to a less than, or a less than to a greater than. But the natural way of solving this one doesn't see that arise at all, right? It just never happens. I never have to divide anything from the a, because right away 3a minus 2a is a single a, and then we can isolate it without ever having to divide both sides. Let's keep going. All right, 14. Ooh, this is the most beastly of all of the multiple choice problems in my humble opinion. You matter. Okay, if you could only see what all of these are. Three functions are shown below. A, g of x equals negative 3 halves x plus 4. B, f of x equals x plus 2 times x plus 6. And C, that parabola. Okay, so let's talk about this. Now, what they want me to do is they want me to compare all three of these functions. And before I get into that, I want to make sure we recognize a few things. One, easy. Letter C, we don't need its equation. We don't need anything like that. We can tell everything we need to from the graph. But B, if we multiplied this out, which we are not going to do, but if we multiplied this thing out, we'd have an x squared, right? Because then we'd have that x times that x, which would give us an x squared. If we FOILed it, all right, side note, we'd get x squared plus 8x plus 12, all right? We don't need to have that. We don't need that, okay? But we'd have also a parabola, right? This would also be a parabola. But this guy, that's the equation of a line, right? And you've been graphing lines now in both 8th grade math and 9th grade math. So you should feel very comfortable that this is a line that's got like a y-intercept of 4, a slope of negative 3 halves. You could even probably do a little sketch of it, right? You could be like, all right, I know I'd have to go up to like 1, 2, 3, 4. I'd have to do my little y-intercept. I'd go down 3 across 2, down 3 across 2, right? Get my line, right? So that's letter A. So it's not that we can't compare A to B and C, but B and C are both living sort of in the same class of functions. They're both quadratic functions, parabolas. They've got graphs that, kind of look like U's, upside down or right side up or whatever, okay? Golden arches. Well, golden arch. All right, but this thing is just a line. Okay, let's take a look at the question itself. Which statement is true? All right, so you actually have to do a lot of processing on this problem to find the right answer. But first, let's take a look at number 1. B and C have the same zeros. All right, we're back to the issue of zeros. Okay, so real quick, let's find the zeros of C. Finding the zeros of C is very easy because we've got its graph, right? The zeros here are x equals negative 4 and x equals negative 2. Those are its zeros. But the zeros of B are also exceptionally easy to figure out. And the reason why is that this thing's written in factored form, okay? And to find its zeros, we can really think about what values of x, when we substitute them into these two parentheses, would result in it equal to 0. And for this, it would be x equals negative 2, and for this, it would be x equals negative 6. Now, they do share one 0 in common, right? They share a 0 of x equals negative 2 in common. All right, but they don't have the same zeros because this one has a 0 of x equals negative 6 and this has a 0 of x equals negative 4. That was a lot of work just to say that choice 1 is not correct. All right, choice 2, A and B have the same y-intercept. Well, let's kind of go back up here. Again, the y-intercept of A is very easy, right? The y-intercept of A is 4, right? It's just there. But what's the y-intercept of B? Well, in order to get this, we simply need to substitute x equals 0 into the equation, and if we do that, what we find is its y-intercept is equal to 12. All right, so do they have the same y-intercept? Nope, this thing's got a y-intercept of 4, this one's got a y-intercept of 12, not the same y-intercept. All right, number 3, B has a minimum, C has a maximum. B has a minimum, C has a maximum. What does that mean? Well, lines don't have minimums and maximums, they just go on forever in one direction or the other, right? But parabolas always either have a top of the hill, like this one. This is a maximum. Hey, there's my red. There, that's a maximum. So the question is, does this thing have a minimum? Because if it does, it's the right choice. Now, multiplying it out like this, x squared plus 8x plus 12 automatically gives us the answer if you remember things about parabolas, right? Now, parabolas, let me kind of get rid of that little bit here so we can see this a bit better, right? Parabolas, whether they open upwards or downwards, are all about the coefficient on the x squared term, and this coefficient is equal to 1. All right, that means this parabola kind of looks something like that, right? It looks like a bowl as opposed to an arch, okay? And this one has a minimum, right? And therefore, number 3 is our winner. B has a minimum, C has a maximum. And again, don't forget, I'm not going to do it now because we've done plenty of graphing at this point, but there's no reason why you can't slap that function into your calculator, graph it, and see whether it's got a minimum or maximum. And you can put it in right like this. You don't need to multiply it out. You don't have to. The calculator will be perfectly happy if your quadratic is in factored form versus standard form. Okay. Oh, a little word problem in number 15. Let's do it. Nikki's sister is 7 years less than twice Nikki's age. A. The sum of Nikki's age and her sister's age is 41. Which equation represents this relationship? All right. Well, first, you must have seen plenty of these things over the last couple years, right? Nikki's sister is 7 years less than twice Nikki's age. Now, you have to be very, very careful with subtraction, okay? If I actually wanted to calculate, if I gave you Nikki's age, if I said that Nikki was 13, and I said, what is her sister's age? And you said, her sister is 7 years less than twice Nikki's age. You'd say, well, okay, if Nikki is 13, twice 13 is 26, and then I'm going to subtract 7 and I'm going to get 19, right? Like, you'd do it that way. So specifically, right, the sister's age, sister who has no name, right, you would calculate by taking Nikki's age, multiplying it by 2, and then subtracting 7. And it is exceptionally important. You do not do 7 minus twice Nikki's age. You don't do that. You know, you'd get a lot of negative ages in that case, but it doesn't matter. The point is, that's not how you do it. If I gave you, right, Nikki's age, and I said, what's her sister's age? You'd go, well, I'm going to take her age and multiply it by 2, right? And then you'd subtract 7 from it. Now, you got to be real careful because, boy, is there an urge right now to be like, okay, so 2a minus 7 is equal to 41, right, which is right here. Right? It is tempting to say 2a minus 7 is equal to 41 because, you know, they gave me a 41. Don't I just take that algebraic expression and, you know, set it equal to that? And the answer is no, right? Because specifically they say the sum of Nikki's age and her sister's age. Well, Nikki's age is a, her sister's age is 2a minus 7. When I add those, I get 41. Now, it should be fairly obvious that the correct answer, therefore, is choice 2. You might object a little bit and say, but wait a second, choice 2 has a parentheses around the 2a minus 7, whereas you don't. The plain fact is, these parentheses are doing absolutely nothing other than basically just kind of separating Nikki's age from her sister's age. But they're not doing anything, right? Parentheses generally say, well, this is one quantity, and if there's a number sitting outside of it, it means that everything inside of the parentheses should be multiplied by that number. But there is no number sitting outside of that except for the number 1, right? So these two are equivalent expressions. Let's keep going. Excellent. Number 16. The population of a small town over 4 years is recorded in the chart below, where 2013 is represented by x equals 0. Population is rounded to the nearest person. Well, that's good. It'd be horrible if they didn't. I mean, if it's really the population of a town, would you really be rounding it to the nearest person? That seems weird. We had a third of a person, but we rounded it down. The population p of x for these years can be, okay, I'm going to stop laughing now, can be modeled by the function p of x equals a times b to the x, where b is rounded to the nearest thousandth. Which statements about this function are true? All right, so this is a great question because it made me laugh, 1, and 2, because it's all about how you form an exponential function, right? We've been talking a lot about linear and exponential functions, and exponential functions generally have formulas, and I kind of like it when they put a multiplication symbol or something like that between the two, but whatever, equal to y equals a times b to the x. Now, in any exponential function written that way, the a is the y-intercept, which is unfortunate because in linear functions, the b is the y-intercept. But here, the a is the y-intercept, also thought of as the starting value, the starting output. The starting output value. Okay, that's the output that you begin at, right? And right away, that's fantastic because that tells me that a is equal to 3810. All right. Always, 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 a is your starting value. It's your value when x is equal to 0 or t is equal to 0 or whatnot. So a is 3810. Now the b is what's called the growth or the decay factor, depending on whether the population or whatever you're modeling is growing or decaying. In this case, the population is growing, and so b is a growth factor. A growth factor. Now, how do you calculate b? Well, thankfully, in Algebra 1, it's actually quite easy. All right? In further courses like Algebra 2, it'll be more of a challenge. But in Algebra 1, it's actually typically pretty easy because these x values, and they really are x values, are separated by 1 unit each, right? This is x equals 0, x equals 1, x equals 2, etc. All we have to do is take 2 consecutive ones and divide them. Now, it's really important to divide the second one by the first one. In other words, the b is going to be 3943 divided by 3810. Let me pop over to our Texas Instruments TI Inspired calculator. Here we go. And let's do that. We got 3943 divided by 3810, enter, and it gives me the fraction again, and there it is, 1.304908, etc. And that's our growth factor. Please notice, right, if the exponential function is increasing, then this number should be greater than 1. And if it's decreasing, it's less than 1. And that's important because if you flip this fraction, if you did 3810 divided by 3943, you'd get the sort of the reciprocal of this, and it would be a number less than 1. All right, coming back over here, right, b is 1.035, and so it's got to be 1 and 4. Now again, side note, I was able to find pretty much that exact value of b by just doing this division. And I could have actually done this division and this division, all of which would have given me a number when rounded to 1.035. They're all slightly different though, and maybe that's where they rounded to the nearest person. That still doesn't make sense even with that, but I'm trying to figure it out for them. The plain fact is, by the way, b could never have been 0.035. It just couldn't have. 0.035 means that it would be a decreasing exponential function and the population would have been going down. You can have populations go down. Populations go down all over the place, and sometimes that population goes down exponentially. In fact, during the pandemic, right, we've actually seen cases increase exponentially at times, and now we're really on the down slope of the decreasing portion. Thank goodness, by the way, because it allows us to resume things like Regents tests and math. But the plain fact is if b had been 0.035, it would have been a decreasing exponential function, and that clearly wasn't. All right, let's take a look at another factoring problem, number 17. When written in factored form, 4w squared minus 11w minus 3 is equivalent to which of the following? All right, now, you had to factor a lot of trinomials during this class, I'm sure, and many of them, the leading coefficient, right, the coefficient that was multiplying the x squared or the w squared or the c squared or whatever was equal to 1. And those tend to be very, very easy. Here, we really want to just multiply each one of these 4 choices out to see if we get this. Now, that's a lot of work, but we don't have to do all that work. And that's because, right, hopefully you've all heard of foiling, right? Foiling is an acronym that says that when I multiply 2 binomials out, I multiply the first terms, the outer terms, the inner terms, and the last terms, and then I combine like terms. But one of the things that I hope your teachers pointed out, right, is that really the f just gives us this, the L just gives us this one, and then it's the O and the I that together combine to give us the middle term. Now, why is that important? It's important because in every one of the 4 choices, the F and the L are correct. They are, right? Like if you look at these two, you get 2w times 2w, which is 4w squared. 1 times negative 3 is negative 3. The f and the work in each one of these cases, it's all about the oi, right? It's all about the oi, the oi, as my people would say. So the thing is, all we really have to do is evaluate the outer and the inner, add them together, combine them, and see if they give us negative 11. See if they give us negative 11. So it's all about outer, inner, giving us negative 11. Actually, I'm gonna keep that. Right? I need this negative 11. So for instance, if I looked at this first one, right, the outer would be 2w times negative 3, which is negative 6w, 1 times positive 2w, which is positive 2w, and that's negative 4w. So the O and the I in choice 1 combine to be negative 4w, but I need them to combine to be negative 11w, and they don't. Right? If I looked at choice 2, again, I don't need to look at the F and the L. They have nothing to do with this problem. 2w times 3 is 6w. Negative 1 times 2w is minus 2w. That's 4w, and again, I'm looking for negative 11w. So that is also not correct. Let's take a look at number 3. In number 3, I've got 4w times negative 3, that's negative 12w. I have positive 1 times w is positive 1w. Negative 12w plus 1w is negative 11w. After a while, w sounds weird to me, and that's our winner. Right? There it is. I don't even need to check number 4, right? So this problem is really getting at the idea that really at its essence, when we have a trinomial, amongst all of this stuff, when we have that original trinomial, we can see whether or not 2 binomials have it as a product by just multiplying them out. Okay, let's take a look at a very calculator-driven problem in number 18. Which ordered pair does not represent a point on the graph of y equals 3x squared minus x plus 7? All right, so I mean, this one's simple in essence. Sorry, as I talk into my lemonade there. This one's pretty simple in essence, right? How do you ever tell whether a point lies on the graph of whatever function? It doesn't matter whether it's a quadratic, a linear, an exponential, whatnot, right? And it's very simple. If I put in, let's say in choice 1, x equals negative 1.5 into this expression, do I get 15.25 out as the y? And you can certainly you can write all this out. You can be like, all right, let me take a look. Let me see what happens when I put, this let's see what happens when I put this, and I type it all into my calculator, and I make sure I get it all right and see if it works out, right? But most modern calculators have a very simple way of doing this. And let's kind of review how to do this. Very similar on the TI-83 and 84 as on this. You can use what's known as the store button. Okay, and again, that's in different places on different calculators, but it allows us to store a value in X and then type out an algebraic expression and see what that's equal to without having to actually substitute the value of X in. All right, I'm going to close this thing out so it's not so messy. No, we're going to reopen a new one. Well, no, I got it right there. All right, here we go. So like that first point was negative 1.5, 15.25. So I'm going to type in negative 1.5. And then on the TI Nspire, there's my store button. It's always this little arrow. It's always the number first, then the arrow, then the variable. I want to store negative 1.5 in X. Now, right now, the calculator thinks that X is negative 1.5. If I type in any expression with X right now and calculate it, like for instance, if I just say, hey, what's 2X? Right? It says negative 3 because 2 times negative 1.5 is negative 3. And for as long as I have, until I change what value is stored in X, until I do that, anything I type in with X is going to give me the value I get when I plug negative 1.5 in. So now let's type out that more complicated expression. And that was specifically 3x squared minus x plus 7. All right, and that's 15.25. And that was exactly the point, right? So the point was negative 1.5, 15.25, that one's on the graph. Now we're unfortunately looking for the one that is not on the graph. So we have to kind of do that for each one of these. Now, again, the calculator makes it even easier than just what we did. For instance, let's take a look at that second one, 0 and 7.25. So now I want, not 0, I'm sorry, 0.5. 0.5, I'm going to store that in X, enter. Now this depends really on your calculator, but on the TI Nspire, I can go up until I get to that expression highlighted. I can hit enter. It then copies that expression. I hit enter again, and there's my 7.25. So now, when X was 0.5, this expression was 7.25. Therefore, that point also lies on the graph. It actually ends up being choice 3 that doesn't lie on the graph. So choice 3 is 1.25, 10.25, 1.25, 10.25. So if I do 1.25 and I store it in X, and then I walk a little bit up my calculator screen until I get my expression again, notice 1.25 has a Y value of 10.4375. It's close, but close doesn't count. Points are infinitesimally small, so this point, or at least the point 1.25, 10.25 does not lie on the graph. All right, let's get back to it. Oh, I should circle the right answer. By the way, if we did number 4, we would find that point does lie on the graph. Okay, number 19. Given the following 3 sequences, choice 1, 2, 4, 6, 8, 10, ... Choice 2, 2, 4, 8, 16, 32, ... And choice 3, A plus 2, A plus 4, A plus 6, A plus 8, ... Which ones are arithmetic sequences? All right, this is cool. Arithmetic sequences are very similar to linear functions. Arithmetic sequences are basically the equivalent or a specialized linear function. Now, what does that mean? That means that all arithmetic sequences have something in common, and that is to go from one term to the next term, you always add the same amount. Now, let's take a look to see if that's true in choice 1. In choice 1, to go from 2 to 4, you would add 2. To go from 4 to 6, you would have to add 2. To go from 6 to 8, you'd have to add 2. To go from 8 to 10, you'd have to add 2. So that is an arithmetic sequence. I add 2 each time to get to the next term. All right, well, let's take a look at choice 2. Choice 2, to go from 2 to 4, I add 2. This is getting a little redundant. To go from 4 to 8, I add 4. Oh, I'm going to just stop right there. To go from 2 to 4, I added 2. go from 4 to 8, I added 4. That's not a linear, I just about said that's not a linear function, and it's not. But that is not an arithmetic sequence, okay? Because I didn't add the same amount to go from the second term to the third term as I did to go from the first to the second, that's out. Which also means, by the way, anything that involves 2 is out. Which means it's got to be choice 2. I don't even have to look at number 3. And again, it's a little bit unfortunate because that's A plus 2, A plus 4, A plus 6, A plus 8. And it's like, oh my God, A. But if you think about it, I'm still just adding 2, right? To go from A to A plus 2, I add 2. To go from A plus 2 to A plus 4, I add 2, right? Because 2 plus 2 is 4. To go from A plus 4 to A plus 6, I add 2, etc. I actually kind of wish they didn't always have to do it add plus 2. It could have been A plus 4, A plus 8, A plus 12, A plus 16, etc. And it would have also been an arithmetic sequence, right? Arithmetic sequences aren't about adding 2 each time. It's about adding the same amount each time or subtracting the same amount each time. All right, we are almost done with the multiple choice. We're not quite there. Let me take another drink real quick. And let's take a look at number 20. A grocery store sells packages of beef. Good to know. The function C of W represents the cost in dollars of a package of beef weighing W pounds. The most appropriate domain for this function would be... All right, let's talk about these. By the way, the answer is none of the above. But that's okay. Okay, they make mistakes. So really, what this is boiling down to is a couple different things. One, what is the domain? All right, well first, let's talk about that. The domain are the inputs to the function, right? And the inputs are always this variable. They're the ones that are sitting in here. In other words, it's the weights, right? It's the weight of the beef that you're buying. The weight of the beef. The weight of the beef. That sounds funny. So it's the weight of the beef that you're buying, right? And so the question is, which one of these sets of numbers would be best suited as the domain, okay? Now that means that we can't have any weight, right, that doesn't make sense as a weight. Well, the first one is integers, right? And the integers are all these whole numbers, but they could be both positive and negative. So, the integers are things like, -5, -4, -3, -2, -1, 0, 1, 2, 3, and oops, wow, I don't know what happened there, but I like it. Let's go back, or I don't like it. Anyway, right, I think that we can all agree that you can't have a beef weight of -4. Right, it just can't be, okay? So the integers would not be the appropriate domain here. All right, well, rational numbers. Rational numbers, we talked about these before, are numbers both positive and negative, and that's enough to say that's not the right answer. Rational numbers are numbers that are both positive and negative, right, that then have decimals that terminate, right, or repeat in some predictable way. But keep in mind, rational numbers aren't just numbers like 2/3 or 1/2. They also include things like -1/3 and -7/5. These are all rational numbers. And again, there's nothing wrong with having 2/3 of a pound of beef or 1/2 of a pound of beef, unless you're a vegetarian or vegan, then there's definitely an issue. But these two, right, no, not allowable. And they're definitely rational numbers, so we can't have that. Now, we're going to start restricting ourselves to just the positives, right? The positive integers and the positive rational numbers. Well, the positive integers, right? Well, yeah, I mean, that's a little bit better, right? 1 pound of beef, 2 pounds of beef, 3 pounds of beef, 4 pounds of beef, etc., right? Those would be the positive integers. But the problem with that is it doesn't allow any fractions whatsoever, right? It means you could buy 1 pound of beef, 2 pounds of beef, 3 pounds of beef, 4 pounds of beef, but there'd be no way to buy a 1/2 pound of beef or 2 3/4 pounds of beef, right? You couldn't do that, but you could do it if you brought in the positive rational numbers, all right? Now, my personal belief is that the correct answer to this problem is the non-negative real numbers, All right. In other words, as soon as you say the positive rational numbers, it means you can't have any irrational weights of beef. And I mean, I think that we could all have irrational weights of beef. But you could certainly have pi pounds of beef. That would be fine, right? You could also have 0 pounds of beef, right? That could be part of the domain too. You just didn't buy any beef at all, and therefore the cost is 0. So my personal opinion is if this was a free response problem, the correct answer would be the positive real numbers. But barring, or sorry, the non-negative real numbers, because we'd include 0. But barring all of that, the best of the 4 choices is the positive rational numbers. That, because we can't have negatives. I think we can all agree on that. But as well, we want those rational numbers so that we can have fractions of a pound. All right, and without them, the positive integers only allow us to have whole numbers. Okay, I have no room to do number 21. I guess I can't do that one. No, I got to do 21. Because 21's our quadratic formula problem. We got to have a quadratic formula problem. I think everyone can agree on that. Let's get rid of this. Okay, so let me got to erase a little bit of that. Okay, there's plenty of room. 21. The roots of x squared minus 5x minus 4 equals 0 are which of the following? All right, so you saw a lot of different techniques to solving what are known as quadratic equations. Those are equations where the highest power is like x squared or w squared or whatever, right? The highest power is 2, but there's definitely a squared term in it. All right, but there were lots of different ways to solve those. One way was to factor and set each factor equal to 0. That's that connection between the factors and the zeros. Other ways were using the technique of completing the square. We're going to see that a little bit for finding the vertex of a parabola. Okay, but the catch-all, this will work every time, no exceptions whatsoever, is what's called the quadratic formula. And let's do that, especially because 2 of the answers kind of make me think about the quadratic formula. Now remember, the quadratic formula says that if we're going to solve an equation that looks like this, ax squared plus bx plus c is equal to 0, say it with me everybody, x will be equal to negative b plus or minus the square root of b squared minus 4 times a times c, that looks like an e, all divided by 2 times a. Let me make sure that's a c. There we go. So there's our quadratic formula. Now, this only works if the equation is set equal to 0. So let's identify the values of a, b, and c. In this case, our a is the coefficient on x squared and it's equal to 1. Oftentimes a is equal to 1, but it's not always equal to 1. B is equal to negative 5. You have to make sure you have that negative along with the 5. And C is equal to negative 4. So now what we're going to do is we're literally going to kind of plug and chug. We're going to say that x is equal to negative 5, negative b, plus or minus the square root of negative 5 squared minus 4 times 1 times negative 4. There's a lot of negatives in this problem. You got to be careful. Divided by 2 times 1. Okay? Now I'm going to erase all of this in just a moment, but again, let's just compare it, right? We have to know this formula. They're gonna put choices up here that are gonna mess us up if we don't know this formula, okay? So we've got it, right? We've got our A, B, and C. We've substituted them all into the formula. So now I'm gonna get rid of this so I have a little bit of room to write. Okay, so what do we have? Well, a negative is a positive. All right, negative 5 squared is 25, not negative 25, positive 25. Negative 4 times 1 times negative 4 is positive 16. You can do a lot of this on your calculator. I'm doing much of it in my head. 25 plus 16 is 41, and that denominator of 2. By the way, you know, if the square root of 41 had been a nice number, you know, like the square root of 36 or the square root of 49 or the square root of 64, you get it. If 41 had been a perfect square, then we could have simplified this further. But that's as far as we can go with it, which means the correct answer is choice 2. All right. We are back to a calculator problem. Let's look at 22. The following table shows the heights in inches of the players on the opening night roster of the 2015-2016 New York Knicks. All right, so these are the heights in inches of the players on my team, the New York Knickerbockers. Go Knicks, great year. Shout out to the New York Knicks and all fans of New York Knicks. If you're a fan of the Atlanta Hawks, you should just stop watching right now. I just don't even want to talk to you. Anyway, but we got the heights of the New York Knicks. I think back in 15, 16, they still had Melo. They probably had KP. You know, they still were not as good of a team as they were this year. Anyway, what we want to do is we want to find the population standard deviation of this data set. And this is a real calculator-driven problem. And again, it's a little bit unfortunate that I can't stand here and show you how to do it on every calculator that you could possibly have, but the best I can do is really show it to you on the TI Nspire, right, without taking up too much time. So let's go over there. Okay, I'm going to close out this window and we're going to then do a little bit of stat. On the TI Nspire, that means that we're opening up the equivalent of a spreadsheet. It's like working on Microsoft Excel if you've ever done that. What I'm going to be doing is I'm going to be putting in all the data into column A. That's going to take me a little bit of time, but I'm pretty fast. I just got to make sure I don't mistype it. Hopefully not. But watch me, and you know, if I got it wrong, I'm not sure how you'd let me know, but it's a nice idea. I just have to be careful. Hey, there's somebody my height. Standing 6'2" and playing for the New York Knicks. I mean, I might be able to do a good job at point guard, but I think Derrick Rose has it. I still believe in you, Alfred. All right, so we've got our data in. Of course, it never hurts to check it over, right? We could have botched it. You know, it's easy enough to like just put stuff in incorrectly. I do encourage you to kind of go through, make sure you've got them all right. Okay, assuming I have them all right, at least on the TI Nspire, I'm then going to hit Menu. I'm going to go to Statistics. I want to do stat calculations, and I want to do one variable statistics. That's all good. Number of lists is just 1. Enter. My list is in A. Hopefully the stuff you're all comfortable with. And then all my statistics show up right here. All right, they're right here. So the question is, what's the population standard deviation? Well, this X with a little bar above it, that's the mean. That's the average, right? Add them all together, divide by how many there are. There were 13, and you get an average of 79.69. So that's not what we want. We want the population standard deviation. There are two types of standard deviation. There's a sample standard deviation, and there's a population standard deviation. Note to self, or note to all students out there, most of the time, the questions actually are addressing sample standard deviation. But this was the population of the players, so I guess they went with that. The sample standard deviation is this little s. The population is this little Greek symbol sigma. It's actually a lowercase sigma. And that's 3.947. I do like the fact that in this problem, they didn't have one of these as this and the other choice as this. That would have been just out and out mean, okay? But in fact, right, the right answer is 3.49, okay, or closest to 3.5. None of the other ones are even in the ballpark, right? One thing that could throw you off is the 79.7 is the mean of the data set. The 80 is likely the median, right? Neither one of those you should confuse, given that you've been seeing mean and median literally since 6th grade. Literally, I know. I wrote a book on 6th grade math. Mean and median were in there, right? So you wouldn't want to pick those. The 13, yeah, I don't know. That's not right, but the 3.5 is it. Keep in mind that the standard deviation, right, is a measurement of kind of how far on average a data point is away from the mean. So, you know, on average, the heights are about 3.5 inches away from the mean of 79.7. But really, at the end of the day, this is a pure and simple calculator problem. Let's look at another exponential model. Problem number 23. A population of bacteria can be modeled by the function f of t equals 1,000 times 0.98 to the t, where t represents the time since the population started decaying, and f of t represents the population of the remaining bacteria at time t. What is the rate of decay for this population? Whew, that's a lot of words. Now remember, right, we talked a little bit about these exponential functions having y equals a times b to the x, right? So what do we know, right? We know that the initial population is 1,000, and that has nothing to do with the problem, right? And then every time our variable goes up by 1, we multiply what we had before by 0.98. 0.98. Which means every time we multiply, we have 98% of what we had before, right? And then we multiply by 0.98, and we have another 98% of what we had before. And if you think about it, if you keep having 98% of what you had previously, you're going down. And you're going down specifically by 2% each time, right? The rate of decay is 2%, not 98%. We're not going down by 98% each time. That would mean we'd like go from, 100 down to 2, right? And that wouldn't happen. I mean, think about this as being 100 instead of 1,000. We'd have 100, then we'd have 98, and then we'd have whatever 98 times 0.98 is, et cetera, et cetera. But we're going down by 2% each time, okay? 24. Bamboo plants can grow 91 centimeters per day. It's true, they grow very quickly. What is the approximate growth of the plant in inches per hour? All right, so this is a unit conversion question. It's a unit conversion question, right? We want to go from 91 centimeters per day to something inches per hour. All right, so here's how I like to do these. I'm going to write down 91 centimeters per 1 day, all right? And somehow I gotta finally get something in inches per 1 hour, right? I gotta get from here to here. And what I wanna do is I wanna multiply by fractions that are basically equal to 1, right, in terms of units. So here's what I mean by that. Let's first deal with the time, days to hours. Now, one thing that we know for certain, right, is that there are 24 hours in 1 day. These are literally the same thing. So what I can do at this point is I can take this thing and I can multiply by 1 day in the numerator, 24 hours in the denominator. Now, why did I do it that way instead of having the 24 hours up here and the 1 day down here? Well, for 2 reasons. One, I want the days to cancel. Just like we cross-cancel in any other fraction, I really want these 2 to cancel, and I want to be left with hours in the denominator, right? Now, likewise, I want to end up with inches in the numerator, so I have to know some equality between centimeters and inches, okay? And I can do that if I don't know it off the top of my head, which I do because I've been in this business for a while. I can go all the way, maybe I can't. I can go all the way to the end of the test. It's probably easier for you than me. Hello, free response questions. We're just about getting to you. Oh, there they are. Oh, there they are. Look at that. Hey, look, it's the quadratic formula. So this little sheet is the catch-all, end-all sheet for every Regents math exam, which is really unfortunate because it's got a bunch of stuff on it you don't need. All right, I mean like a bunch of stuff, okay? Including most of the gobbledygook up here, I mean, I wish I had this when I was cooking, Then I could at least look at some of these things. But at the end of the day, all we need is the fact that 1 inch is equal to 2.54 centimeters, and then we'd have to get back up to my problem. There he is. Yes. All right, so what do we know? We know that 1 inch is equal to 2.54 centimeters. Now remember, I want inches in the top, and I want centimeters in the bottom so that the centimeters cancel out. So I'm going to do 1 inch and 2.54 centimeters. And again, the centimeters are going to cancel, and they're going to leave me with inches. Whew. Now, after all that was said and done, what is this calculation actually telling me to do? It's telling me to take 91 and divide it by 24, and also divide it by 2.54. I'm going to take 91 and divide it by 24, divide it by 2.54. Let's go over to the calculator real quick, and let's ax this out. Nope. Let's get our calculator, and let's do 91. And I like doing this in stages. I'm going to do 91 divided by 24. And it does that fraction thing, right? And now, almost every calculator will allow you to take your previous answer, and then I'm going to divide that by 2.54. And there it is, 1.4927, right? So that's 1.4927, but we'll just round it right there, 1.49 inches per hour, right? Every unit conversion is done that way, right? You have some kind of an equality, and you take that equality and you form a fraction. And believe it or not, each one of these fractions is actually equal to the number 1. It doesn't look like the number 1. It looks like the number 1/24 and 1 2.54. I don't know what that is. But anyway, but it's not, because 1 day and 24 hours are equal to each other. So it's just multiplying by the number 1. That's just multiplying by the number 1, but in these kind of tricky forms. All right, hey, we are done with the multiple choice. Let's do some free response. We're actually done with the vast majority of the problems now, right? Now, the exam, if you're just trying to pass it, is won or lost on the multiple choice. You know, you can pick up a lot of problems, obviously, in the free response, but the multiple choice is where you really earn the bulk of your points. So make sure that when you get done with the multiple choice, right, you take a breather, maybe go back, check over them, or maybe work on the free response, then go back to the multiple choice. Don't leave any of them unanswered. You're not penalized for answering a question incorrectly because you've guessed. You know, the conventional wisdom is, you know, eliminate, you know, ones that you can, and if you don't have any idea, then guess, right? But now, let's take a look at the free response. All right, now the free response begins on every algebra exam with quite a few 2-point problems. Now these are basically supposed to be the equivalent of a multiple choice problem except without the choices. We'll see whether or not that's true. Some of these 2-point problems are going to be very, very easy, and some of them are going to be more challenging. And very often we get one like problem 24, which is actually, you know, just solve this equation, but then they want to like throw you off with fractions. So let's take a look at this equation. Solve algebraically for x. -2/3 times the quantity x plus 12 plus 2/3 x is equal to -5/4 x plus 2. Now, conceivably, you could have been asked to solve this problem in 8th grade math, right? It's just basically a linear equation with variables on both sides, but of course it becomes more intimidating because of the fractions. Let me take a little drink of lemonade and then let's do it. Oh, so good, so refreshing. All right. Anyway, so let's take a look. Now, conventional wisdom says the first thing I should do is really get rid of these parentheses by distributing the -2/3 x through the parentheses. Now, -2/3 x is pretty easy, but then you've also got -2/3 times 12. Now, I can do this by hand, and you're supposed to be able to do this by hand too, but for goodness sakes, if it's any problem for you, right? Don't hesitate to come over to your calculator, right? There's -2/3 times 12, and I get -8. There's no reason to push that issue. Again, yes, we can cross cancel, we can talk about negatives times positives and all of that. But at the end of the day, you can also just do it like that if you have to. All right, so we have -2/3 x minus 8 plus 2/3 x is equal to -5/4 x with some stuff like that, plus 2. All right. Now, oftentimes after we've used the distributive property like that, we'd like to combine some like terms on one side or the other. Then we'll get to things like the addition property of equality, but we're not there yet. And right away, one thing that's nice about this is that we've got a -2/3 x, a positive 2/3 x, and those are what are called additive opposites. They're just going to cancel each other out. I'm not adding two things to the same side or anything like that. I'm just combining those two like terms. That's equal to 0. So we get -8 is equal to -5/4 x plus 2. Okay. Now what I'd like to do is isolate this x. So I'm going to subtract 2 from both sides. That's going to be pretty easy. Let me bring it up. I'm going to get -10 is equal to -5/4 x, right? That's going to cancel. -8 minus 2 is -10. And now I have to get rid of the negative 5/4 x. Now again, this is an issue of how comfortable do you feel with fractions, right? In theory, I can divide both sides by negative 5/4. I can totally do that. I can do negative 10 divided by negative 5/4. The conventional way of solving this is not to do it that way, but to multiply by the reciprocal of that fraction, all right? And it's got to be a negative 4/5, all right? Because then a negative times a negative is a positive, and literally we just get all this like cross-canceling, and that leaves us with x. Now we have negative 4/5 times 10. And again, one can do that if you just know how to like say, well, you know, 5 cross cancels into 10 gives me a 2. Now I have negative 4 times negative 2, and that gives me x equals positive 8. Or you could go to your calculator and do negative 4/5 times negative 10. Again, conceivably, you could even way up here say x is equal to negative 8 divided by negative 5/4. That is a little bit harder to pull off on the calculator. You'd have to be a little bit careful with parentheses and stuff like that, but you could do it. All right, so x equals 8. It is not unusual for them to throw a linear equation at you as a 2-point problem that like back in like middle school would have been like a 4 or 6-point problem. Sometimes they'll even mix decimals with fractions. It can get ugly, okay? Don't be scared to use your calculator and make sure you check your answers. All right, let's take a look at one that is far less messy. Number 26. If c equals g minus 3 times f, find the trinomial that represents c when f is equal to 2x squared plus 6x minus 5 and g is equal to 3x squared plus 4. All right, this is pretty simple. Really what they're looking for you to do is to combine like terms and simplify polynomials and things like that. So let's take a look. They tell us that c is equal to g minus 3 times f. Don't get freaked out by that. Right, f, like g is 3x squared plus 4 minus 3, get some parentheses in there, right? All of f is getting multiplied by negative 3, not just the first portion. It is critical that you've got these parentheses around here. If you've got the 3 without the parentheses, right, you're going to lose a point just immediately. And it's only a 2-point problem. You know what I mean? If you make 2 mistakes, it doesn't matter what else you do. You know what I mean? It just doesn't matter. So get those parentheses in there. Without the parentheses, it means the 3 is only multiplying the 2x squared, and it's multiplying all of f. It doesn't say negative 3 times just the beginning part of f. It's negative 3f. All right. Next thing that we're going to do is we're going to take this and we're going to distribute it through, and we're distributing not just the 3, but also like the negative 3, right? We want to bring it all through. All right, negative 3 times positive 2 is negative 6x squared. Negative 3 times positive 6 is negative 18x. And here's the kicker. Negative 3 times negative 5 is positive 15. Be very careful with that. Okay? Now what we want to do is we want to combine like terms. Okay, we have 3x squared and negative 6x squared. 3x squared, negative 6x squared gives us a net negative 3x squared. The only x to the first term is this one, and that's a negative 18x. And then we have 2 constant terms, a positive 4 and a positive 15, and those combine to be a positive 19. And there's our trinomial. 3 terms, trinomial. 1 term, 2 terms, 3 terms. Okay, let's take a look at another one. See, that had no fractions in it, some negatives, but no fractions. All right, a piecewise function. Let's take a look. Graph the following piecewise function on the set of axes below. F of x equals the absolute value of x when x is greater than or equal to negative 5 and less than 2, and negative 2x plus 10 when x is greater than or equal to 2, less than or equal to 6. All right, well look, first, before we graph the piecewise function, let's just make sure we understand the idea of graphing functions, right? Functions, again, are these rules that you put a value of x in and you get a value of y out. And when you do that, you put an x in, you get a y out, you create a coordinate pair that must lie on the graph. Now, piecewise functions have more complicated rules because they say, look, you know, the first rule is y equals the absolute value of x, but that only applies here. So let's actually kind of create a table of values really quick for that. Right, we got x and y, so we're going to start at -5, and the absolute value of -5 is 5. And then the absolute value of -4 is 4, the absolute value of -3 is 3, -2 is 2, -1 is 1, this is getting boring. The absolute value of 0 is 0, the absolute value of 1 is 1. And now I'm going to put a little star by this one, right? That's what I would call our cut point or our transition point. In other words, that's where we go from one formula to the next one. And the 2 really isn't included in this formula, but I want to have it in this table anyway. So let's actually plot these points, and then we'll come back to the second formula. All right, so this is going to give us that classic absolute value look. We're going to go out to -1, 2, 3, 4, 5. Go 1, 2, 3, 4, 5. -4, 4. -3, 3. -2, 2. -1, 1. 0, 0, 1, 1, and now remember that 2, 2 is not really there, so I'm going to leave it as an open circle. Now, let's fill this in. Okay, it is absolutely critical because for years you've been told, oh, extend your line and put a little arrow at the end of it. Don't do that. Not in this problem. This formula only goes from x equals -5 to x equals 2. If I draw an arrow that goes off to the left, that means I'm implying that that function continues past the x equals -5 to values like x equals -6, x equals -7, etc. And it doesn't. All right. Again, keep in mind that I've put the circle on the 2 because the 2 is really not part of this. Now you might say, well, why didn't you just stop at 1? X equals 1. If I did that, I would leave out this little bit between x equals 1 and x equals 2, which this formula still applies to. Now let's take a look at this one. All right, this formula. So this is y equals -2x plus 10. Now that's actually the graph of a line, that's the formula of a line, but I don't really even need to know that particularly, right? I just want to start chucking some values in here. I'm going to start with 2. Now I'm going to do these in my head, but -2 times 2 is -4, plus 10 is 6. And I'm going to put 3 in here. -2 times 3 is -6. -6 plus 10 is 4. Right? If I put 4 in here, -2 times 4 is -8. -8 plus 10 is 2. If I put 5 in there, -2 times 5 is -10. -10 plus 10 is 0. And if I put 6 in there, which is the last value, -2 times 6 is -12, plus 10 is -2. Side note, just to review this yet one more time, this portion of the function is a linear function. And notice, for constant changes in x, when I add 1 to each x, look what's happening to y. It's decreasing or going down by 2. That's just that slope, right? -2x. It's -2 over 1. For every 1 that I go over, I go down 2. 1 over, down 2. Okay, let's plot these points. So I have the point 2, 1, 2, 3, 4, 5, 6. This time I'm going to fill it in because it's part of the formula. 3, 1, 2, 3, 4, 4. And I can actually do this very quickly because I know my slope is -2. So I'm just going down 2 units each time. I connect that with a nice straight line, just like what I mentioned before. Make sure you do not extend arrows past in both directions, or in either direction for that matter. Either way, they would -1. This is a lot of work for 2 points, right? I mean, and you could see how easily those 2 points could vanish. One way is you filled in this dot, or maybe you stopped early, or you put those arrows, or what you have you, right? It can be tricky. Just pay attention, plot each portion of the 2 formulas separately. Make sure you watch that cutoff point. That cutoff point is going to be part of one formula or the other. It can't be part of both. It can't be. If it was, this wouldn't be a function, right? Because then that cutoff point, x equals 2, would have 2 outputs for 1 input. I try to get the review in where I can. Let's take a look at the next problem. Oh, this one's sweet. 28. Solve 5x squared equals 180 algebraically. Okay, so the first thing I want to note is this is an equation. Let me write it even bigger so you can really see it. 5x squared equals 180. This is an equation that has an x squared in it. All right, that's important. Every equation that has an x squared in it, in theory, has two solutions. Two solutions. Now, what you'll learn and talk about in Algebra 2 a lot more is that those two solutions could be the same. They could be like x equals 1 and x equals 1, all right? But most of the time, the two solutions are two distinctly different numbers. Now again, we talked about earlier, we saw a multiple choice problem, right? Where we solved a quadratic using the quadratic formula. I would not advise that here, right? We can actually solve this particular quadratic by just using inverses. In other words, the first thing I'm going to do to get x all by itself is I'm going to divide both sides of this equation by 5. Why not? That 5 is just there and not doing much for me. 180 divided by 5 is 36. All right. Now I can invert the squaring process by doing its inverse, which is the square root. And it would be very easy to then write down x equals 6 and be like, I'm moving on to problem 29. But again, it goes back to the fact that there are two answers here. Not just x equals 6, but also x equals -6. And that's true, right? I mean, if I took -6 and I put it into the original equation, this one up here, I did -6 squared, I'd get 36. Then if I did 36 times 5, I'd get 180. Okay? Very important, when you take a square root to solve an equation, when you take the square root of both sides of an equation, it always ends up in a plus-minus scenario. X equals +6, x equals -6. Okay. That was the kind of two-pointer I like. Oh, a blizzard. Awesome. Let's talk about 29. A blizzard occurred on the East Coast during January 2016. I think I actually remember that. Snowfall totals from the storm were recorded for Washington, D.C. and are shown in the table below. Which interval, 1 a.m. to 12 noon, or 6 a.m. to 3 p.m., has the greatest rate of snowfall in inches per hour? Justify your answer. Well, number one, I'm going to have to say grammatically this problem is just problematic. One, we're comparing two things, so it should be which one has the greater rate of snowfall, not greatest rate. That would be if we had three intervals we were comparing. The other one is like which one has the greatest rate. This was back in 2016. Which one had the greatest rate of snowfall? Anyway, guys, just watch your editing. We all make mistakes. I get it. Anyway, it's very important to understand that this is the total amount of snow that's fallen. So at 1 a.m., there was 1 inch of snow that had fallen. By 3 a.m., a total of 5 inches had fallen. By 6 a.m., a total of 11 inches had fallen, etc. And that's very important because when we think about this, right, let's take a look at 1 a.m. or 1 a.m. 1 a.m. to 12 noon. Noom. Talking about mistakes, right? 1 a.m. to 12 noon. It's important to understand that we're not dealing with 33 inches of snowfall between those two times. We're actually dealing with 32 inches of snowfall, right? Because we already had 1 inch on the ground, right? And then we had 33 inches of ground on the ground. So we actually had 32 inches of snow that had fallen, right? 33 minus 1. Now, how much time had passed, right? That's the whole point of a rate. How many miles per hour? How many cookies per minute did Kirk eat, right? A rate is an amount typically per unit time. Well, how much time passes between 1 a.m. and 12 noon? And that's a little bit tricky to think about, right? If it was 12 a.m. to 12 noon, 12 p.m., right, that would be 12 hours. Here it's just 11 hours, right? So we got 32 inches in 11 hours, which is ugly, but let's go over to our calculator really quick. Let's do 32 divided by 11. All right, and give me that fraction again. So that's going to be, let's say, 2.91. Let's round to the nearest hundredth. 2.91 inches per hour. Now you might say, well, why did I round to the nearest hundredth? The problem didn't tell me to round. Well, remember, we're just doing this by comparison purposes. It could be that maybe I didn't round, maybe I should have more decimal places. Well, it'll depend on that second interval. So let's take a look at that second interval. The second interval, right, which is 6 a.m. to 3 p.m. Let me go back up here. right? Let me get rid of these arrows. So now we're talking about 6 a.m. to 3 p.m. Again, it's very important. I don't care about 36 inches of snow sitting here. I care about how much snow fell between these two times. We had 11 inches on the ground, then we had 36 inches on the ground, so we had 25 additional inches of snow, right? 36 minus 11, 25 inches of snow fell between those two times. Now, how much time was there? Well, to go from 6 a.m. to 3 p.m., these are the kind of problems you did back in like 3rd grade. But if you think about it, right, 6 a.m. to noon would be 6 hours, plus another 3 hours, right? We're talking about 9 hours. And again, another a little bit obnoxious division problem here. 25 inches fell in 9 hours. So let's do 25 divided by 9, and I'm going to go right for it, right, is 2 point, that's not right. Let's try that again. 25 divided by 9. Like, I think they're a lot closer. There it is, right? 25 divided by 9, 2.777, etc., right? Maybe I'll round this also to the nearest hundredth. That's going to be 2.78. 2.78 inches per hour. I do actually kind of like the messiness of this problem because it is messy, right? Not just grammatically incorrect, but it's also messy, right? We got 2.91 inches per hour, 2.78 inches per hour. It's now completely acceptable that we rounded this way. Even if we were rounded to the nearest tenth, this would have been 2.9, that would have been 2.8, and it would have still given us the correct conclusion, right? Which was, which has the greatest rate of snowfall, or greater rate of snowfall, and that would have been 1 a.m. to 12 noon. Never forget to actually answer the problem. 1 a.m. to 12 noon had the greater of the two snowfall rates. Average rate of change. Ooh, a cone. Let's take a look at 30. The formula for the volume of a cone is V equals 1/3 times pi r squared h. Solve the equation for h in terms of V, R, and pi. All right, so this is one of these problems where you got a formula, it's got a bunch of letters in it, a bunch of different variables, and you have to get one of them all by itself. So let me write this thing out in larger form. Now, the first thing that's really important to understand is which variable you're solving for, right? And there's 3 variables. There's V, there's R, and there's H. 1/3 is a number, and so is pi. But whatever. There's V, there's R, and there's H. And we're solving for H. In other words, we want to get this thing all by itself. Okay. Well, one thing that's kind of interesting to note is what is happening to H. Really understand it. In this formula, H is being multiplied by 1/3, by pi, and by r squared, right? This is just one giant product. 1/3 times pi times r squared times h. And to remove multiplication, you just divide. To make this problem look a little bit nice, let's kind of at least get rid of the 1/3, not by dividing, but by multiplying both sides by 3. That gives me 3v is equal to pi r squared times h. Now, right, keep in mind again, this is all a product over here. And I can really kind of think about this almost in terms of the associative property of multiplication. I can almost think about just grouping those two, right? Those two things are multiplying h, in which case to get rid of them, I'm just going to divide by pi r squared. And that gives me this as my formula for h. H is 3 times v divided by pi r squared. Now, I will say for the record that they should give you credit in this problem if you said h is equal to v divided by 1/3 pi r squared. All right, now granted, that's what's known in math as a complex fraction because there's a fraction within a fraction. And generally, we don't love complex fractions in math simply because, quite frankly, this is a prettier formula. In math, we would call it a more elegant formula, all right? But at the end of the day, this and this are algebraically equivalent, and so you would think that they would have to take both of those two answers. Your math teacher might not like that, but they really should take both answers. All right, let's take a look at problem 31. This is what's called a recursive sequence problem. Given the recursive formula, a sub 1 equals 3, and a sub n equals 2 times the quantity a sub n minus 1 plus 1, state the values of a2, a3, and a4 for the given recursive formula. Ugh, this looks really complicated, and it's actually really, really simple. Look, sequences, which is what we're trying to produce here, we're trying to produce the second, third, and fourth terms of a sequence, right? Sequences are just numbers that are in a line, right? They're just like the first number, the second number, the third number, the fourth number, etc., right? And this rule tells us how to produce the numbers. And it says, well, the first number is 3. A1 is the first number. And then it says to calculate any other number, a sub n. What you're going to do is you're going to take 2 and you're going to multiply it by the previous number plus 1. All right? So, if I want the 5th number, I'll take the 4th number, add it to 1, and multiply by 2. Right? If I want the 18th number, I'd take the 17th number, add it to 1, and multiply by 2. Now, I don't need those, but what I do need is a2. And specifically what this rule tells me is that a2 is 2 times a1 plus 1, just the number before it, right? And now I just do a little substitution. a1 is 3, right? Then that's going to be 3 plus 1 is 4, and 2 times 4 is 8. Right? All this rule says is to produce the second number, we're going to take the first number, add 1 to it, and multiply the result by 2. And that's how I get 8. Right? To get the third number in my sequence, I'm going to take 2 and multiply it by the second number plus 1. And my second number was 8. That's what I just figured out. That's going to give me 2 times 9, and that's going to be 18. And finally, my fourth number is going to be 2 times my third number plus 1. The numbers are starting to get a little bit larger here, but that's okay. I could always use my calculator if I need to. 2 times 19, and that's going to be 38. And that's it, right? So a recursive definition for a sequence basically tells you how to calculate each term based typically on the term right before it. All right. Oh, are we moving up? Nope, not quite. Here we go. Determine and state the vertex. All right, let's take a look at this. Determine and state the vertex of f of x equals x squared minus 2x minus 8 using the method of completing the square. All right, I want to get a little caught up on my notes here. I've been so carried away. All right, so let's take a look at this. Now, one thing about this type of problem is that they're very specific. They want you to find the vertex or the turning point of this parabola using a particular method. Now, what wouldn't hurt at all is actually putting this thing in your calculator, graphing it, finding the vertex and going, well, okay, I know that's my final answer, right? Now, how do I get it using completing the square? One of the many rules on the Regents exam is that, in general, if you find an answer to a problem using a method that is not what they specify, you can still get up to half credit. Now, this is a 2-point problem. So you could say, well, I graphed it on my calculator. Here's a little sketch of the graph. The vertex is blank. And I think they'd still give you 1 out of 2 points. All right. But to get 2 out of 2, we have to do it by completing the square. All right. So let's talk about completing the square. Now, I'm going to write this down as y equals instead of f of x, just so I don't have to use function notation. The idea behind completing the square is always a little bit weird, and it's very algorithmic. It's step 1, step 2, step 3 kind of thing. But here's step 1. Step 1 is you take a look at the coefficient, the number that's multiplying x to the first, and that's negative 2. All right, that's b, right, in our A, B, C thing. And what we're going to do is we're going to take that and we're going to divide it by 2. No matter what that number is, we're going to take it and divide it by 2. So negative 2 divided by 2 is negative 1. Then we're going to take that number, that negative 1, and we're going to square it. Negative 1 times negative 1 is 1. All right. So what do I do with that? Well, what I do with it is I tack it on to that x squared minus 2x. I put a plus 1 there. Now, golden rule is you can't just like randomly add something, right? So you got two choices at this point. You could put a plus 1 also on the other side. That's completely okay. Many teachers do that. The way that I teach it is I say, well, one thing I can add anytime a 1 is 0. So I can add 1 and subtract 1 at the same time, and that actually doesn't change anything. That's just adding a whole lot of nothing. But I also don't want to forget the minus 8. Right? Now again, this expression and this expression are identical. All I've done is tucked a little 0 in right here, 1 minus 1. Threw a little 0 in. Nobody minds a little 0. But the point of completing the square is that this trinomial is now a perfect square. It can be factored into a binomial times itself. And specifically, right, what it can be factored into is x minus 1 squared. These two then combine, -1 and -8 are -9. Okay? This is what's known as the vertex form of this parabola. And that takes us back all the way to, I think, problem like number 4, when we had f of x equals x minus 2 quantity squared plus 4, and g of x equals x minus 2 quantity squared plus, or x minus 5 quantity squared plus 4, and here's our vertex, here's our vertex. The point is, this parabola is just this parabola that's been shifted right 1 and down 9. Okay? But your standard simple parabola has a turning point at 0, 0. This thing then will have a turning point at 1, 9. Sorry, 1, -9. I apologize for that. And that's it. Again, completing the square is kind of algorithmic, and once you have it, then saying, oh, okay, what I did was I took this parabola and I shifted it 1 unit to the right and 9 units down. And yeah, that's a little bit weird, right? When we subtract from x, we shift to the right. When we add to x, we shift to the left. And then the number that's sort of hanging out here, right, plus 7, minus 9, whatever, that's shifting up and down in the direction you'd expect it to. All right? Without getting too much more into vertex forms of the parabola, let's go on to part 3. All right, so the Common Core Algebra exam has 4 parts on it. The first part is the multiple choice, by far the longest, right? Just multiple choice questions. Then you get part 2, which is all these 2-pointers, right? And then you get part 3, which is some 4-point problems. So let's take a look at our first 4-point problem. Number 33, a school plans to have a fundraiser before basketball games selling shirts with their school logo. The school contacted 2 companies to find out how much it would cost to have the shirts made. Company A charges a $50 setup fee and $5 per shirt. Company B charges a $25 setup fee and $6 per shirt. Boy, that's convenient. The first part of the problem, write an equation for Company A that could be used to determine the total cost A when X shirts are ordered. Write a second equation for Company B that could be used to determine the total cost B when X shirts are ordered. All right, you've probably seen plenty of these problems where there's some kind of fixed cost and then a fee per shirt, per hour, per brownie, per whatever, right? And it's actually pretty easy because these are linear equations, right? The fixed charge is the y-intercept, and then the rate, $5 per shirt and $6 per shirt, is the slope. So for A, it's very simple, right? For X t-shirts, we would have $5 times the number of shirts we sell, plus that $50 setup fee. For B, we'd have $6 times the number of shirts we order, plus the $25 fee. Now, there's nothing wrong with flip-flopping the addition. Addition is what's known as commutative. So I could easily rewrite it as 50 plus 5x and 25 plus 6x. That's a great way to think about it. But typically we write the sort of the x portion first and the fixed part second. But there you go. Let's take a look at the second part. Determine algebraically and state the minimum number of shirts that must be ordered for it to be cheaper to use Company A. All right, so let's take a look at this. We want to determine algebraically the minimum number of shirts so that it's cheaper to use Company A. Well, what should we set up for that? It's actually an inequality, right? Because this is how much it costs to order X shirts from A. This is how much it costs to order X shirts from B. So what I want to do now is I want to say, hey, I want to figure out when this cost is less than this cost, right? This is truly an inequality, and you really, really do have to have it set up as an inequality. Now let's solve the inequality. And here, that little thing about inequalities where you divide both sides by a negative is going to come out. So first things first, let's get all the x's on one side. I'm going to subtract a 6x from both sides. All right, be careful. 5x minus 6x is negative 1x. Many times we won't write the negative 1, but I'm going to in this case. Plus 50 is less than 25. I'm going to subtract 50 from both sides. All right, that's going to leave me with negative 1x is less than 25 minus 50 is negative 25. And now, to get x by itself, I'm going to divide both sides of the inequality by negative 1. That's going to flip the inequality, and x is greater than 25. Now, I'll have some students who really know what's going on, and they'll say, well, why didn't you just subtract 5x from both sides, get all the x's over here, subtract 25 from both sides, etc.? Absolutely. Do it. It works great. Okay? In that case, what you'd get is you'd have something that looks like this, if you did it in that order. And those two are the same thing. Let me move the little hand there, right? You'd get this if you chose to isolate the x's on this side and isolate the numbers on that. I wanted to do it this way just to illustrate this idea that when we divide both sides by a negative, we have to flip the inequality sign. Now, at the end of the day, though, we're not done. We wouldn't want to move on to the next problem because it says, determine algebraically and state the minimum number of shirts that must be ordered for it to be cheaper to use company A. Well, what this answer says is it says, hey, as long as we order more than 25 shirts, it's cheaper to use company A, which means the minimum number we have to order in order for it to be cheaper is 26, not 25. 25 would actually be where the two companies' costs are the same, right? 26 is the first time when A is cheaper to use than B. And that's because, quite frankly, B has a much lower startup cost. So you have to order 26 shirts before A is cheaper. All right, graphing problem. Let's take a look at 34. Graph y equals f of x and y equals g of x on the set of axes below. F of x equals 2x squared minus 8x plus 3, and g of x equals negative 2x plus 3. Fantastic. Let's take a look. So the first thing we have to do in this 4-point problem is we have to produce graphs of this function and this function. Now, one thing I'd like to note before we get into the graphing and the calculators and all of that is that this first function is a parabola, right? It's a quadratic function. It's going to have some kind of U shape or some kind of arch shape. In this case, it's going to open upwards because its leading coefficient, the number multiplying x squared, is positive. It's positive 2. But this function is linear. This is the equation of a line, negative 2x plus 3. There is no way I'm putting that in my calculator and asking it to graph for me. All right, this one I'm going to produce a table on my calculator. This one we're going to do the old-fashioned way. So let's first go over to the calculator and see how we can generate a table to get some values. All right, I'm going to grab my sheet here. Let's close this thing out. Nope, and let's add a graph. Okay, I'm going to put in, I know, let's see, here we go, 2x squared minus 8x plus 3, make sure it looks good, enter. Now, it's all good and well to have this, right? Oh, lovely, awesome, right? But I need a table of values. I need points that I can plot on my grid. And all graphing calculators have a way of putting in a function, right, and generating a table of values. On the Inspire, of course, there's a particular way of doing it. I'm going to go over to Menu. I'm going to go to Table. Like, where's my table? Split Screen. Okay. And here it is. Let me go up a little bit. It's right. Here we go. So we've got our x coordinate and our y coordinate. So when x is negative 2, y is 27. When x is negative 1, y is 13. When x is 0, y is 3. When x is 1, y is negative 3. I can just scroll down to get the other values. Now, my grid paper actually only allows me to go up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It actually does allow me to go all the way up to 13. So let me go back over here, right? I could create and should create a little table of values. You know, maybe I have it right here. I'd have my X, my Y. I would just be copying these off the screen, -1, 13, 0, 3, 1, -3, 2, -5, 3, -3. It's good to write down your table of values so your teacher or whoever is grading your test, oh my, I don't know what's going on there, can see what you're doing. And now we're just going to plot those points. So -1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 0, 1, 2, 3, 1, -3. Let me move this up a little bit. 2, -5, 1, 2, 3, 4, 5. 3, -3. Notice the symmetry on the Y values, 4, 3, and 5. Let me do this count one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There we go. A very narrow parabola. I'm gonna have to shrink this a bit. Come on. Nope. There it is. Kind of. Come back to me. Ha. Excellent. Nice and smooth curve. Technology. Nice and smooth curve. This is one of the worst looking curves. All right, -3 right there. Okay, that's my parabola. Try to get it through all the points, you know what I mean? Make sure when you draw a parabola, it's a nice smooth curve. Do not take your ruler out and draw a straight line, then another straight line, then another straight line, then another straight line. Believe it or not, that's a 1-point deduction. Anyway, so you could now certainly put this one into your calculator and generate a table of values as well. But keep in mind, right, this is a linear function with a y-intercept of 3 and a slope of -2, and I'll write it in fraction form, over 1, right? So I should be just plotting my y-intercept at 3 and then going down 2 to the right 1, down 2 to the right 1, down 2 to the right 1, rise over run. So let's do it. So we're going to plot our y-intercept at 3, go down 2 to the right 1, down 2, right 1, down 2, right 1. We could reverse that in the opposite direction. And then with a ruler, which I do not have the capability of doing, we're then going to draw those arrows. Now let's get some finishing touches here. Before we answer the second part of this problem. Okay, one thing I definitely need to do that I haven't done so far is I need to label my graphs. I absolutely have to label them, okay? If I don't, then I will have a 1-point deduction for not labeling their equations. I could just label them F and G. There's nothing wrong with that. In other words, this is f of x and this is g of x. But you have to be clear about which one's which. It's also just good form. You should say, this is this function, this is this one. Now there's the second part of this problem, right? Determine and state all values for which f of x equals g of x. I'm sorry, I didn't quite read that right. Let's go to the board for just a moment. Determine and state all values of x for which f of x is equal to g of x. I want values of x. All right. Now I'm trying to be very, very clear about that because a lot of students know what they're looking for here. They say, oh, I know what's going on, right? I'm supposed to find these intersection points. This is like a system problem, right? And I got this one intersection point at 0, 3, and then I have this other intersection point at 3, -3. But I want to be very clear about this. Those aren't values of x. Those are coordinate pairs. The answer to this problem are these two values of x. X equals 0 and x equals 3 are the x values where the y values of the two graphs are equal. And that's what it's really saying. What x values are there where the two y values And that's what f of x and g of x are. They're y values where they're equal. And those are 0 and 3. So be very, very careful about that. Don't get me wrong. You could certainly have a question that says, at what points do the two functions intersect? But that's not the issue here. The issue here is what are the x values where the two functions intersect. All right. Another calculator-driven problem. Let's take a look. 35. The table below shows the number of hours 10 students spent studying for a test and their scores. Write the linear regression equation for this data set. Round all values to the nearest hundredth. All right, so you've been doing scatter plots and lines of best fit for a couple years now, but the graphing calculator now allows us to put in all of this data into two lists and ask it to come up with the line that best fits the data. And again, this is very particular to what calculator you're using, although there are certainly similarities between the TI Nspire and the TI 84 and 83, but the way you do it on a Casio or a Hewlett-Packard or anything else might be a little bit different. So let's head over. Let's get rid of our current window. Let's put in a table. And what we're going to be doing is we're going to, in the first column, we're going to enter that first row. So that's going to be 0, 1, 2. We have 3 4s. Right? 4 gets entered 3 times. I'm saying that more for me than you. 2 6s, a 7, and an 8. All right. Now we're going to go back up. And in column B, we're going to put the other numbers, 35, 40, 46, 65, 67, 70, 82, 88, another 82, and a 95. Excellent. All right, yet again, it's very, very critical that you go back and you make sure you've entered this correctly. Given that this is completely a calculator problem, it's going to be spitting out the answer for you, right? In the TI 83 and 84, you're doing this within lists, what are called lists, all right? But it's still the same thing. In fact, you can actually see more of the values in those. But now, let's get that linear regression equation. I'm going to hit Menu. I'm going to do Statistics. I'm going to go Statistical Calculations, and I'm going to do Linear Regression. All right, now this one's not quite set up right. I need my first one to be A. I need my Y list to be in B. All right, I've got everything is okay there, and there it is. What do you mean there it is? Where is it? Uh-oh. It's kind of hard to find it on here. On the TI, it's actually quite easy, the TI 84 and 83. But you got to kind of go up a little bit, and what you find is here's the regression equation, m times x plus b, where the m value is 7.79220, etc. And the b, so the slope is this, and the b, the y-intercept, is this. Now they asked us to round both of these to the nearest hundredth. So our final answer in terms of the equation itself is simply going to be y equals 7.79x, don't forget the x, it's wrong without it, plus 34.27. Can't tell you how many times people write the equation of the line as like 7.79 plus 34.27. But as soon as you don't have an x in there, all you have is a horizontal line. You have a constant y value. Otherwise, x isn't even involved. Now, 2 more things in this problem. The second part says, state the correlation coefficient of this line. The correlation coefficient to the nearest hundredth. The correlation coefficient has another name. It's also called the R value. All right? So again, that's purely calculator. There's nothing we can do about that. But the beautiful thing is, it's sitting right here. The R value is 0.9817, etc. Watch out, you don't want the R squared value. That's used in upper level statistics a little bit more. We just want the R value, we want it to the nearest hundredth, that's 0.98. So 0.98. All right. Now the final thing is explain what the correlation coefficient suggests in the context of the problem. Well, let's make sure that we just understand what the correlation coefficient means in general, right? The correlation coefficient basically tells us how well does the line fit the data, or even better yet, how well are the y values predicted by the x values, right? How well is the correlation? All r values go between -1 to 1, all right, with both an r value of -1 and an r value of 1 being perfect fits. The difference between those is if the r value is negative, it means it's a negative correlation. There's a negative relationship. But this is an r value that is very close to 1. Very close to 1. 0.98 and 1, very close. So what the correlation coefficient suggests in the context of this problem is that the amount of time, the red's coming out all over the place here. The amount of time studying is a good predictor of the student's grade. I think that there's like some kind of moral to this problem. Like, study more and you'll get a better grade. Surprise! You probably know that if you're actually watching this video right now. Anyway, the point though here is that an r value that's very close to 1 or close to -1 means that one of the variables, the x variable, predicts the y value very well. You could phrase this in other ways. You could possibly say that the line of best fit fits the data really well, but that's not there's really no context to that. Do you know what I mean? You could say simply that the the linear association between time spent studying and the grade on the test is very strong. But at the end of the day, it's really about how well we can predict the output given that we know the input, right? And that R value of 0.98 means that the hours spent studying was a great predictor of what grade the student would get. Okay. A system of inequalities. Let's talk about a system of inequalities. 36. A system of inequalities is graphed on the set of axes below. Let me just pan this up a little bit. State the system of inequalities represented by the graph. Then we're going to state what region A represents. Then we're going to state what the entire gray region represents. This is a weird systems problem. Anyway, before we actually figure out what the system of inequalities represented by the graph is, let's actually figure out what the equation of these two lines are, both the dashed line and the solid line. And for the moment, let's not worry about the fact that this line is dashed and that line is solid, although it's definitely going to come into the problem. So I just want to write the equations of these two lines. Let's start with the dashed line. One thing I can note on the dashed line is it's got a y-intercept of 3, and it's actually got a slope, well, that was almost right. It's got a slope of -3, all right? In other words, right, we go to the right 1 and down 3, to the right 1 and down 3, to the right 1 and down 3. So this thing has an equation y equals -3x plus 3, right? Its slope is -3, its y-intercept is 3, that's its graph. They weren't very original in this problem because then this other line, right, I'm going to get rid of all these. This other line has a y-intercept of -2, and then it's got a slope of 2 because you go to the right 1 up 2, to the right 1 up 2, to the right 1 up 2. So this thing has got an equation y equals 2x minus 2. Okay, so now, what is the actual system of inequalities? Well, one thing I want you to notice is that on both of these, the shading is below the line. And that can be a little bit tricky for some kids to see, right? But if you just think about it, right, it's definitely below the line. If it was raining, right, it would hit the top of the line, this dashed line here. It wouldn't hit this stuff that was like shaded here. And the same is true over here. What that means is that both of these inequalities involve a less than symbol, right? But The dashed one is what's called a strict inequality. It's simply y is less than 3x plus 3, negative 3x plus 3. This one, because it's solid, will include an equals as well. So our system of inequalities is y is less than negative 3x plus 3, that's my dashed one, and y is less than or equal to 2x minus 2. Again, the equality on this one, because the line is solid, just less than on this one because the line is dashed. Now, what does A represent? Well, A is where the gray shading intersects this kind of cross-hatching. A is literally the solution to the system. That's it, right? A is the solution to the system. I mean, we could get fancier than that, but that's it, right? And when you did these kind of problems, when you graph them, which you probably did a lot more than like a problem like this, right? When your teacher would say, put in a giant capital A for the solution to the system, you would find where typically the two shadings intersected, and you'd put a large A there. Now, you probably either had two of them that were cross-hashed or two of them that were shaded. You probably didn't have a cross-hash and a shading, but what are you going to do? You know, it's a state test. Now finally, and I find this a little bit odd, it says, state what the entire gray region represents. What does the entire gray region represent? Well, let's go back to this. What is the gray region? They just want me to talk about what this is. Well, that's simply the solution to this single inequality. That's it, right? A is the overlap between the two. So it's the solution to the system, right? System solutions are where both conditions are met, right, together. That's here, right? But the gray represents the solution set to y is less than or equal to 2x minus 2. Again, interesting. I had never seen a systems problem like this, but it's kind of cool because you can really answer these second two portions of the problem without ever being able to write this down. You know, you could have gotten this all sorts of wrong, and you could still get these two right. Don't get me wrong, this is a 4-point problem. 1 point, 2 points, 3 point, 4 point. Do you know what I mean? So you want to get those 2 points right, but you can certainly get the other ones. And here we come to it, the last problem of the evening. Now let's back up just for a moment, right? As I mentioned before, we've got 4 sections on the exam. Multiple choice, part 1. Part 2, short, real short problems, 2 pointers, but still free response. Part 3 were those problems we just did, those were 4 pointers. And finally, a single 6-point problem, which often boils down to 3 2-point problems, which is exactly what this one did. And let's take a look at it. It's a classic, right? Number 37. When visiting friends in a state that has no sales tax, good to know. It's like New Hampshire. New Hampshire has no sales tax. 2 families went to fast food restaurant for lunch. The Browns bought, definitely New Hampshire. The Browns bought 4 cheeseburgers and 3 medium fries for $16.53. The Greens bought 5 cheeseburgers and 4 medium fries for $21.11. There is no diversity on this test. Using C for the cost of a cheeseburger and F for the cost of medium fries, write a system of equations that models this situation. You know, if you did systems of equation problems, then you see this one and you're like, yes, right? Because you did a million of these, or at least you did a few of them, right? So let's take a look at it. All right, the Browns bought 4 cheeseburgers and 3 medium fries for $16.53. That's one equation right there. Why? Because we're going to take 4, we're going to multiply it by the cost of a cheeseburger. We're going to add to that 3 and multiply it by the cost of 1 fry. Not 1 fry, but 1 set of fries. I hope I don't have to buy them by the fry. And we're going to get $16.53. Right? On the other hand, the Greens bought 5 cheeseburgers plus 4 fries and they spent $21.11. You know, it's interesting because I'm not sure who's getting the extra fry in both cases. It's probably me, probably not. I'm probably going to order fries. My wife is going to say she doesn't want any, and then she's going to have half of mine. No offense, honey. Anyway, so let's take a look at the second part of this problem. I'm really probably dead when I go inside. The Greens said that since their bill was $21.11, each cheeseburger must cost $2.49, and each order of medium fries must cost $2.87 each. Wow, that's funny. Each cheeseburger must cost $2.49, and each order of medium fries must cost $2.87 each. I think there's one each too many there. Are they correct? Justify your answer. I can't imagine how the Greens did this. They sat there with their single equation and they were like, I don't know, you know? I mean, it's not like the menu's in front of them with the costs there, but let's see if they're right. And it's really simple to see if they're right, right? All we have to do is put $2.49 into the right equation for a cheeseburger, and then we got to put $2.87, right, in for the fries. It seems weird that the fries cost more than the cheeseburgers, but whatever. Good fries, you know, and see if it's equal to $21.11. So let's check it out. So we're going to do 5 times $2.49 plus 4 times $2.87. And of course, we're just going to do that on our calculator. I'm not going to waste your time by going back to the TI. But that gives me $23.93. Now, they paid $21.11, and so the answer is no. By the way, the interesting thing about this problem is if the answer was yes, we wouldn't even do the last part, right? Because the last part is going to actually ask us to figure out how much a cheeseburger was and how much fries were. So if the Greens were right, we'd be like, hey, just talk to the Greens. You know, it'd be over. So the answer is no. But it's good. It's good to be able to check to see if your answer is actually correct. So now, let's solve this algebraically. I'm going to have to rewrite the system down here. All right. So 4c plus 3f is equal to 1653. And then 5c plus 4f is equal to 21.11. So this gets into how do you solve a system of equations. Now, the way that you learned this year that was new, so you learned multiple techniques, but the way that you learned this year that was new was what was called the method of elimination. And that works when you add the two equations together and one of the variables gets eliminated, either the c or the f. But the only way that that can happen is if you have additive opposites. So you have two things that are opposite each other, like -10 and +10, or -6 and +6. And right now, quite frankly, if we added these together, we'd have 4c plus 5c, which would be 9c. We'd have 3f plus 4f, which would be 7f. We need them to go away. All right, which means the first thing we need to do in this problem is manipulate the two equations using the multiplicative property of equality. There you go, the multiplicative property of equality. And by that, what I mean is we're going to multiply both sides of one equation by some number and both sides of the other equation by a different number to produce opposites. And the only issue for us is, what do we want to eliminate? Do we want to eliminate the c's? Or do we want to eliminate the f's? And that's all about what you decide to multiply by. I decided to eliminate the f's, okay? So what I'm going to do is I'm going to take this first equation and I'm going to multiply it by -4, okay? And I'll explain why I'm going to do this in a moment. I'm going to multiply both sides of this equation by -4, and it is really important that you multiply both sides by -4. And that's going to give me -16c minus 12f, and then I'm going to, on my calculator, do the 1653 times -4. I mean, I don't like math that much. And I'm going to get -66.12. Now, I'm going to come back, and on this equation, I'm going to multiply both sides by +3, right? So I'm going to do that because that's going to end up giving me a +12 that will be able to cancel out that -12. So 3 times 5c is 15c. 3 times 4f is +12f. That's what I really wanted. And then 2111 times 3 is 63.33. And now I'm going to add these two equations together. right? And again, what I want is I want two things that are opposite. So let's be very clear. I could have multiplied this first one by positive 4, giving me a positive 12 here, and then multiplied this equation both sides by negative 3, giving me a negative 12. That would have been great, okay? Or I could have been like, I want to eliminate the c's, in which case maybe I would have gotten this one to be a negative 20c and this one to be a positive 20c. All of it would work, all of it will give you the same answer. When I add these two equations together, I'm going to have negative 16c plus positive 15c. Those are going to give me a negative 1c. These are going to eliminate, and then maybe on my calculator I'll add the negative 66.12 and the 63.33. Either way though, it's going to give me negative 2.79. But that's going to be calculator when I add those two together. Now, I could divide both sides of this equation by negative 1, or I could state the obvious. If negative c is equal to negative 2.79, then positive c is equal to positive 2.79. In other words, right, one cheeseburger costs $2.79. Now, by the way, I want throughout this problem, especially a problem like this, for you to understand whether or not your answers are reasonable. This is a reasonable answer for a couple of reasons. One, it's not negative. There's no way the cost of a cheeseburger is going to be negative. And if it is, that business is going to go out of business by me alone. Okay. Another thing, it's got dollars and cents. There's no extra decimals here. We would never expect to see 2.79834556, right? You don't see that on a menu. That makes some sense. Now let's figure out how much an order of fries costs. How do I do that? Well, I take my 2.79 and I'm going to put it either into this first equation or into this second equation. It shouldn't matter which. So what did I do? I put it into the first equation. So I'm going to take this first equation, and by the first equation I literally mean this one. You know, before I multiplied by negative 4 on both sides. I'm going to do 4 times 2.79 plus 3 times f is equal to 16.53, big decimal point there. 4 times 279 is 1116. Move up our board a little bit so we have a little more room. 1116 plus 3f is equal to 16.53 minus 11.16 minus 11.16. We get 3f is equal to 5.37. I need every bit of room on this one. I'm going to divide both sides by 3, and I'm going to find f is equal to 1.79. And again, that's reasonable, right? That's reasonable. I didn't get extra decimal places. I didn't get f equals 1.7932. I didn't get f was negative, right? And it even kind of makes some sense, like it would have been weird if the cheeseburgers had cost $18 a piece, unless I was in like some fancy like New York City bourgeois kind of restaurant, right? You know, same thing about the fries. The fry price kind of makes sense. All these 79s, that might be a little weird, but whatever, you know, I can buy that. All right, and that's the exam, right? You probably realize, if you've taken practice exams, that there is additional graph paper that I never used. There is that formula sheet that is eventually somewhere here, right? That's got a bunch of formulas on it that you don't need, don't want to pay attention to, although that quadratic formula would have been nice, okay? But besides that, there's not much else on here you need, okay? And that's the exam. Now, I want you to keep in mind, throughout all of this, right, that you've got 3 hours for this exam. Some of you may even have more time than that. Take that time, especially if this exam really matters, right? And you matter. You really matter, right? You matter to me, you matter to your teachers, you matter to your family, okay? And how you do on this test might very well matter as well. This has been an awfully strange year. It's been an awfully stressful year. Probably many of you saw your teachers only about half the number of school days that you would have in a normal school year. Maybe you were remote the whole time. You know, if you were in New York City, you were likely remote the entire year. All right, and there were many, many schools like that, both in New York State and outside of New York. So take your time, take those 3 hours. A lot of the math is repetitious or repeats what you did in 8th grade. Think about that horrible problem we did with solving the equation that involved the fractions, right? And of course, a lot of the math is new, and a lot of it's very specific, like the vertex form of a parabola, or finding the zeros, or understanding the connections between factors and zeros, right? Very specific to Algebra 1. I'm hopeful that going through this test, you got exposed to a lot of the topics that you saw this year, right? And they refreshed many of those things in your head. For all of you that are taking the test tomorrow, good luck with it, right? I have confidence that you can do well if you take your time and you think through all the problems thoroughly. And you will be rewarded for that if you take your time and think thoroughly. But I think that's it for me. I think I'm going to call it a night. So as always, thank you for joining me for eMath Instruction's Algebra 1 Live Regents Review. My name is Kirk Weiler, and until I see you next, keep thinking.